query, and it returns an encryption of 0 if that query is in the data set, and otherwise an encryption of randomness. Now, this is a very common thing in, for example, multi-party private set intersections. But this specific abstraction has not really been shown before. But what's interesting is there are many different ways to instantiate it, and these have been shown before. So encrypted polynomials is one way. You can show that these are optimal in size, but they're very slow to encode and decode. So in practice, they're not really great to use, especially like knowing that the bank's data set is pretty big, right? So it doesn't scale very well. And then there are encrypted Bloom filters. I've worked on these in the past. They're kind of nice, like they're fast to encode and decode, but they are approximate. And actually there are very like subtle security problems with it. And then, so some people in the audience might be aware of this, there are oblivious key value stores. And so oblivious key value stores in many ways resemble already an encrypted membership query filter. Basically what this is it's a key value store, but the values that it stores are supposed to look very random. And because they look so random, you can, like the final structure also looks random. So these are somewhat fast to encode, but they're really, really fast to decode. So these are very convenient. And these are being used in the latest MPSI protocols too. So our solution using EMQFs looks as follows. So this is just the previous high-level overview. And then what we do is we basically have the sending bank and the receiving bank encode their data set as an EMQF and send that to the payment network service. So this happens just once during the setup phase. And then a transaction is split into the relevant data for the sender and for the receiver. And those are, the EMQFs are queried on that data. Then the output is an encryption of yes or no, but and we perform an AND operation. And the way we really go about it is that it's a partially homomorphic encryption of 0 or randomness, and we add up this result. So the result is still 0 or random. So it's still 0 if both are in the EMQFs. So both transactions, both parts of the transaction are considered valid. In the end, we decrypt, but we also randomize, because if you would query on the EMQF with the same query, you get the same result. So you need to somehow re-randomize that so that when you send stuff to the banks, that the banks don't know what you've been querying on. Now, I saved all the interesting cryptography for just one slide. So if you don't care about the cryptography, you can close your eyes right now. So the key idea here was to, we wanted to make it really fast and really compact. Because there are so many transactions that need to be sent to the other side. And so the key idea is to encode elliptic curve-based algomal ciphertext in such an EMQF. Elliptic curve-based because they're really fast and very compact. And so we found that oblivious key value stores provide the best trade-offs. And what's actually interesting to see is that if you use, for example, those encrypted polynomials, the protocol basically reduces to some previous work from Hasse et al. And then if you use the encrypted Bloom filters, it also reduces to another work. So OKVSs, they're new. Now they require the ciphertext to be indistinguishable from random bit strings, and we achieve this by using an alligator map. Finally, this is an optimization that we don't really care about. So our final solution looks as follows. So here's where the ML comes in. So this is the overview we saw in the beginning. We have the EMQFs that are generated on the bank side, and those are sent to the PNS. Then for a query, the PNS queries the relevant EMQFs. The relevant banks perform collective randomization, so each contributes their own randomness. And then there's collective decryption. So the PNS obtains the valid transaction flag. The banks do not get this information. And then some kind of regression is performed. So how does that happen? Well, these are the initial features that we get in this system. And we engineered a few features. So this is basically what we did for the competition. So there's one flag, which is, does the currency match, like the instructed currency match the settlement currency? What is the time between the transaction was submitted and the settlement timestamp? And then there's our cryptographic protocol to obtain this single bit of information, which is whether it's a valid transaction according to the banks. And then we perform some kind of differentially private regression model, and we get a risk score out. Differentially private because we don't want the results of this model to reveal anything about the data it was trained on. So these are the results. So we tried a random forest and linear regression. And then the ones where we say EMQF is where we also incorporate our Boolean feature. Okay. So very quickly, this is the overview. The linear regression is, in the end, the solution that we stuck with, and it was trained using DPSGD. And as you can tell, the EMQF solution does actually work. So the Boolean feature does actually provide better accuracy to the system. So in the end, we won the second place in the PETS prize challenge. But from the top 3 solutions, I think our solution does have the highest security guarantees, but there's some kind of trade-off there. So we proposed a protocol for repeated membership queries. We provided this nice, I think it's a nice abstraction, encrypted membership query filters. And then we provided the first implementation of OKVSs, where we actually put like ciphertext in there instead of secret shares. Thank you very much.
All right. I'll just ask a short or very long question. We'll see. So I was wondering, you said that you added in the differential privacy to ensure nothing could be learned about the training data. I was wondering what you did to verify that.
Yeah, we didn't. So basically, this was the reason why we didn't is that the competition didn't really ask for it. So I know it's not a satisfying answer, but I would say that our main contribution is this, private membership query. And then the competition just asked for it, and this is what we did. So the competition basically said, these are a few different epsilon values on which we're going to evaluate your solution. And then they said, but instead of using epsilon, if you can't do like epsilon differential privacy, you can also give a bound on the advantage on a membership inference attack. I don't think anyone went with that because it's really hard to do.
All right. We can take one more question if there's one in the audience.
Hello. Thank you for the presentation. So it is not really a machine learning question, but rather a question about your implementation of OKVS over the elliptic curve. So can you elaborate a little bit more about that?
Yeah, I agree. Like that's the interesting cryptography part. But yeah, the key behind making an OKVS secure is that the values that you encode in them need to be uniformly random bit strings, right? And so the problem with elliptic curves is that the curve points do not look like uniformly random bit strings. So you somehow need to mold it into a set of bit strings that look just fine. And it's what's good for us is that people have looked at that problem before. And so one solution is the alligator map. So that works for a couple of specific elliptic curves, and we decided to use exactly such an elliptic curve. So what it does is it takes a compressed curve point and then somehow spits out a random looking bit string, and it's also invertible. It only works for half of the points, so you have to do some kind of rejection sampling, but for us, that's no problem. And so then in the end, you obtain the same security guarantees that you get when encoding like secret shares into the OKVS. Yeah.
All right, as the next speaker comes down, let's thank this one. All right, our fourth speaker in this session is going to be Tanado Naka, swap vowels. And he is a researcher at Mitsubishi Electric Corporation, and his talk today is going to, if I recall correctly, to go a bit into a defense as it relates to / aimed at membership inference attacks.
Thank you for introduction. Hello everyone, I'm Tsunato Nakai for Mitsubishi Electric. Today I would like to talk about SEDMA, self-distribution weights module aggregation for membership privacy. This slide shows the overview of this presentation. We propose a new defense method against membership inference attacks, which identify whether a target sample was used in training data. Also, membership inference attacks are important measure to evaluate the potential risk of privacy leakage from trained model. Defenses against membership inference attacks are classified into two categories: probable privacy defenses and empirical membership privacy defenses. Empirical membership privacy defenses aim to preserve the model utilities. So in this presentation, we introduce a new empirical membership privacy defense, named Sedma, which outperform state-of-the-art defenses such as KCD and Selena in achieving the lowest risk of privacy leakage. This is an outline. First, as a background, I explained empirical membership privacy defenses. Next, from the challenges of previous work, I will explain our goals for privacy defenses. Next, I will propose a new defense called Sedma based on self-distribution using model aggregation. In the experiment, we will show the evaluation result of Sedma on the 3 benchmark dataset. Finally, I will summarize this presentation. The defenses against membership inference attacks are classified into 2 categories. Probable privacy defenses provide privacy guarantee, however, degrade model utility. On the other hand, empirical membership privacy defenses maintain high model utility, but cannot provide probable privacy guarantees. In this study, we focused on empirical membership privacy defenses. There are some empirical membership privacy defenses such as AdBreak, MemGuard, KCD, and Selena. The state-of-the-art defenses have achieved good privacy utility trade-off by using knowledge distribution on split training dataset like KCD and Selena. In this study, we propose an empirical membership privacy defense for 3 goals: low attack accuracy, high model accuracy, and low computational cost. For low attack accuracy, we conduct 2 types of attack: single query attack and label-only attack. We conduct 9 attacks in total to evaluate attack accuracy. For high model accuracy, we compared with state-of-the-art defenses, KCD and Selena, to evaluate privacy utility trade-off. Also, it is not practical if the additional computational cost for the defenses is significant. For example, according to Selena experiment in the paper, the 25 trend model are required for good trade-offs. So next, I will explain the KCD and Selena and our defense. Our defense aims to achieve these goals. In KCD, the KCD defense consists of 3 steps. First, KCD make combinations of split training data and trained multiple submodels on each combination. Next, the submodels label the prediction results for each one remaining untrained split training data and make a data set with the label data. It is called soft label. In the inference phase, it output a prediction result by using mitigated model trained on the dataset with soft labels. In Selena defense also consists of 3 steps. First, Selena trained multiple submodels on each split training data and obtained prediction result with the submodels for each one remaining untrained split training data. Next, a model is trained on the data labeled ensemble of prediction result. Finally, in the inference phase, it output a prediction result by using mitigated model trained on the dataset labeled by ensemble prediction result. So based on KCD and Selena, our defense Sedma also consists of 3 steps. First, Sedma trained multiple submodels on each training data and aggregate the submodels in each combination. The aggregate models label the split training data not used for training in each combination. The label data is gathered as a data set with soft label. Finally, in the inference phase, Sedma output a prediction result by using a mitigated model trained on the dataset with soft labels. This is an intuitive expansion of SEDMA for 3 goals. For low attack accuracy, the model aggregation of SEDMA aimed to reduce the overfitting of trained model by smoothing the information of trained data among multiple submodels. For high model accuracy, the model aggregation preserves the model accuracy, such as in federated learning. For low computational cost, SEDMA generates multiple aggregated models by averaging the models with combination of submodels. This is a setup of our experiments. We use 3 benchmark datasets, PETS 100, Texas 100, and CIFAR 100. We use 4-layer MLP model for PETS 100 and Texas 100, and ResNet 18 for CIFAR 100. We conduct 2 types of membership inference attack, single query attacks, label-only attack, in total 9 attacks. We compared with 5 defenses, AdReg, MEMGuard, KCD, Selena, and our defense, SEDMA. We set the hyperparameter of the defenses from each paper for good privacy utility trade-off, like this setting. These are experimental results, 3 data sets and 2 types of attack. The vertical axis is model accuracy and horizontal axis is attack accuracy. The upper left shows the good trade-off between model accuracy and attack accuracy. Our defense SEDMA was superior privacy utility trade-off performance compared with other defenses. Also, these graphs show the processing time during training phase and inference phase. SEDMA has less training time overhead than Selena, but SEDMA, our defense is slightly more than KCD in training phase, but SEDMA has a superior privacy utility trade-off performance than KCD. In conclusion, we propose a new defense method using safe distribution with model aggregation against membership inference attack. Our defense mitigates the overfitting of training data by averaging multiple submodels trained on split trained data. In addition, we achieved low computational costs because our defense aggregates the combination of submodels. We demonstrate that our defense outperformed previous defenses in achieving the lowest risk of membership privacy leakage in comparison with previous empirical defenses such as AdReg, MEMGuard, KCD, and Selena. In future work, we will apply our method to federated learning and large language models. That's all I would like to talk, so thank you very much.
Thank you very much for the talk. I was wondering if you could talk a bit more about how the inference phase works. So for a given data point, is it necessary to make sure that that in the combination model, you're not using one of the split data sets where that data point itself was during training, or if you could talk a bit more about that?
In the inference phase, we use just a mitigated model. So in training phase, we have to split data set and train multiple submodels. But in the inference phase, we use just mitigated model only. I
guess what I meant is during the training phase, you split up into some number of data set partitions, and then when you're evaluating, for example, the membership inference accuracy, probably you used some of the points that were in the training data to see if the adversary. So I was wondering, when you you're going to combine multiple models that were trained on several partitions. So do you ensure that that mitigated model doesn't include a model trained on a data partition where the data came from? Not sure if the question is clear.
Yes, that's a good question. Actually, this is a try and error because our method is actually for the good tradable. We use a seven sub models. It's just hyperparameter, so it's a case by case for task or data set.
Okay, I'll just ask one question, which I think is borderline just an obligatory, uninteresting question for any sort of defense style paper. I was wondering, because I don't think I spotted it in the presentation, what types of approaches you considered in terms of developing your own attack that was informed by how you created this defense, as opposed to, you have number comparisons to other defenses, but specifically, were you able to develop any better attacks versus the ones you were comparing your defense at being successful at resisting?
So you mean what types of attack is
given you designed a new defense, a more clever attacker knows what type of defense strategies you're taking. What approaches did you use to consider what clever attacks could be constructed against your new defense?
It's a tough question. So when I write this paper, we just at 7 attacks, but Rabia said more attacks should be tried. So it's difficult to evaluate the differences.
All right. Now let's thank the speaker. Yeah, it looks good. All right, our next speaker is Chalo Aksus from Case Western Reserve University, where he is a PhD student. And we are going to be hearing a bit more on attacks, but this time from the other side of the coin, where we're actually going to break things again, as opposed to fix them later. Yeah, there we go. Time for breaking things.
Hello everyone, my name is Abdullah Çağlaröksüz, and today I will be presenting you my attack, Autolycus, which is an exploiting explainable AI for model extraction attacks against interpretable models. Before we start, first, what is model extraction attack? It's a type of privacy attack where an adversary tries to obtain a copy or approximation of a target machine learning model through membership queries. What is explainable AI? It's a collection of methods and techniques in AI that helps humans to understand the workings and decisions of machine learning models. And what are interpretable models? They are the types of machine learning models whose inner workings and decision-making processes can be inherently understood and explained by humans. So our motivation is basically cloud service providers like Amazon and IBM offer cost-effective solutions, and those are machine learning as a service platforms which provide customers with pre-trained models or tools to deploy their own. With these platforms, there's a growing demand for explainable AI tools to ensure model decision transparency. However, white box access to models poses significant privacy risks, prompting providers to offer black box access instead. In such cases, explainable AI is essential for justifying and enhancing the utility of model predictions. Nevertheless, explainable AI itself also introduces privacy risks due to the auxiliary information it reveals. There are multiple model extraction attacks in the literature. However, the following factors narrows down our motivation for certain aspects. We want our model extraction attack to steal functionally equivalent models. Therefore, it needs to be fidelity extraction focused. We want our attack to consider the privacy risks posed by model explanations. And since we are considering machine learning as a service platforms under black box access, our explanations must consider local and post hoc explanations. We want our attack to target a range of interpretable models, which are still highly utilized in the industry. Therefore, it should not explicitly focus on neural networks, and it's better to use an explainer tailored for a variety of model types. Therefore, it should be model agnostic and not explicitly focus on neural networks. And when we redact the explainers that are extensively studied, we are left with two of the commonly employed model explainers to target the interpretable models. Here is the system diagram of our attack, but before we start, I would like to list our assumptions. We assume that customers or adversaries have black box access to the target model M through MLAS platform. To prevent incomplete or invalid queries, customers know that samples cannot have unrealistic or missing features. They are also aware of all the possible values or intervals that labels and features can take. Customers have knowledge of the model type, not architecture. Example of this can be decision tree and logistic regression. Let's assume Bob is a customer. For an MLAS platform, he sends a sample xi, and he wants it to be evaluated as a query. MLAS platform checks the validity of the query, and after ensuring that there are no missing or invalid features, it sends it to the model M for predicting the label of xi. MLAS platform also uses M's corresponding explainer to provide an explanation for the model's prediction. After per query fee is charged, MLAS platform sends the label yi together with its explanation generated by the model explainer. But let's assume Bob is an adversary, and Bob has access to an auxiliary dataset DA. He can use this DA to send queries. This dataset is here to prevent blind search, and it can be very minimal. Using this dataset, he does what a regular customer does, but locally he uses a traversal algorithm called TrevA and model explanations as its parameter. Thanks to traversal algorithm, he repeatedly generates new samples to be queried within the vicinity of decision boundaries or important features. With this, Bob aims to create a surrogate dataset DS to retrain a stolen model, basically. And here is our methodology. Start with an initial dataset called DA for auxiliary dataset. Send a query to the target model, M. Parse the predictions and explanations returned. Using the explanations, generate new samples to be discovered by perturbation. We are exploiting the explanation in this regard. Put the newly generated samples behind of the queue. Repeat until the query budget is exhausted, and use the queried samples as a surrogate dataset as a final step. And here is what explanations look like in Lime on the top and Shop at the bottom. And while Lime provides both local decision boundaries and feature importances, Shop only returns the local feature importances for a query sent to the target model. Note that since this is a black box access scenario, we do not consider the importances and boundaries produced for the classes not predicted by the target model. So in this case, for example, orange is the predicted class, but Lime and Shop also returns the boundaries and importances for other classes like apple, black gram, and coffee, but we do not use those since those are not the predicted classes. During our experiments, we evaluated with 6 datasets, most of which are from UCI machine learning repository. The reason why we didn't consider image datasets is that it's already evaluated in multiple neural network studies. Also, the explanations we demonstrated for Lime and Shop are not tailored for image data, and they do not have any utility. here are our settings for the experimental setup. And I just want to point out, fidelity is the model similarity, basically, between stolen model and the target model, and it's first proposed by Florian Tremmer in 2016. We evaluated 5 different types of interpretable models. Although random forests are part of ensemble methods, they can still be considered as interpretable when containing low number of trees. We evaluated our attack against 3 state-of-the-art and 1 baseline attacks. Equation solving and path-finding attacks are proposed in the first model extraction attack paper of Florian Tremmer again. And IVAL attack is proposed by Varun Chandrasekaran for model extraction attack as active learning paper. Before we go, in those against those methods, we only use the reported results under comparable settings, and in those settings, we require less number of queries to extract identical or partially identical models with less number of queries. And here is an example setting for our Lime results. And as we can see, the number of queries 0 corresponds to a baseline attack, which involves not sending any queries whatsoever. And sending queries basically outperforms those. And as we increase the number of queries, most of the time the attack, the stolen model gets more similarity. And the same for SHOP. The smalling, basically the size of the box plot gets smaller in 0 here because n is equal to 5, and n is the number of samples we used per class in the auxiliary data set. Since we have more sample, the initial result is better. And this is our experiment for the number of features, how impactful they are. And as we can see, this is for Lime and on adult income data set for only 3 samples used per class. And as we can see, after reaching to 5, it kind of flattens down. And as we, from this, we can say that 5 features are necessary for getting better extraction in adult income data set. And we proposed 4 countermeasures. Those are, apart from the obvious one, which is limiting the number of queries by the MLAS platform, we proposed rounding confidence values, differential privacy on training data, and differential privacy on decision boundaries, which can be static or dynamic. Firstly, rounding confidence values does not work in our system since we consider only label only. Secondly, applying differential privacy to the training data of the target model makes our attack even easier due to the removal of outliers and reducing overfitting. Thirdly, applying differential privacy on the decision boundaries of Lime dynamically does not hinder our performance. That is due to the removal of noise during the retraining process. Finally, static differential privacy on decision boundaries is the only countermeasure that can lower the performance of our attack, but it reduces the utility greatly compared to the privacy it preserves. Basically, as our final findings, Lime outperforms against SHOP because it additionally contains decision boundaries, which is an information that we can exploit additionally. The number and the distribution of important features impacts extraction performance. And those are the tabulation of the results, which makes the model extraction attack easier as it gets higher, or which makes it harder as it increases or decreases. Model complexity, overfitting, and outliers, as they decrease, the model extraction attack gets easier. For the other factors, it's vice versa. And our contributions are as follows. We have minimal requisites to deploy this attack. We do not rely on exact reconstruction like the previous studies, and it allows us to partially reconstruct for lower query budgets. To the best of our knowledge, this is the first model extraction attack that exploits AI explanations for targeting interpretable models with black box access. And again, to the best of our knowledge, this is the first model extraction attack that exploits model agnostic AI explanation tools. And here's the QR code for our code and paper. Thank you for listening.
Thanks for the talk. In the beginning, you said that your auxiliary data set can be minimal.
Yes.
Can you say a bit more on what minimal means? What sizes did you consider?
For example, in this adult income data set, for example, for this is line, when n is equal to 1, I don't know if you are familiar with, I'm sure you are probably familiar with the adult income data set. It predicts whether certain individual makes a salary annually above 50K or below 50K. And it only has 2 classes. You make either above or below. And when n is equal to 1, you just need to have 2 samples, basically, one from making above 50K and one below 50K. And you can use that as an auxiliary data set to start the algorithm.
Okay, does that generalize to other data sets that you need one sample per class?
The difficulty of attack changes, depends on the number of samples. For example, in nursery dataset, actually, since the distribution is, it's not a sparse model, basically. So you need more samples, actually, to reach similar, let's say, 1,000 queries for extracting the full model. But for more simpler models, n is equal to 5 is usually enough.
Okay, good. Thank you.
Can you show that if the number of queries goes to infinity, that in the end you end up with the same?
Actually, because of the runtime issues with the Lime and Shop, they are painfully slow to extract. We limited the number of queries to 1,000, but later on the stage, we implemented some solutions with 10,000 queries. And most of the data sets, I think, apart from the adult income data set, they are like fully extracted, but we did not reported those results in our paper.
I have a possibly dumb question. In your adult income data set results here, what is going on in logistic regression and naive Bayes with that first variance?
Between the 0 and the others, or?
Yeah.
0 is baseline. Basically, you are using only the 2 samples for building a stolen model, basically. And as you send more and more queries, you get more data and you create a more accurate stolen model, basically. And this is like the, I forgot to mention, we had 10 surrogate dataset examples, and this is a box plot of 10 samples.
Okay.
10 different collection of samples.
Do you have any hypotheses as to why you're seeing such differences across your samples for that data set versus your nursery
Some
data set?
samples really reflect the decision boundary of the target model really well. So it's actually like a hyperparameter optimization. So if you pick great samples, you can make this attack way shorter. But if you pick terrible examples as your initial data set, it can take forever.
Great, thank you. Let's thank the speaker. All right, our final speaker in this session is going to be Yuzhen Yun from the National University of Singapore, where he's doing his PhD. And we are going to now add in GANs to the eclectic mix of MLAI MPC we've had going on today. And specifically, we're going to see a variant of the work focusing primarily on vertically partitioned data.
I am Yuan Xun, and this work is cooperated with Mr. Yang sitting there and Dr. Ayan, and this work is supervised by Dr. Prasanna Gop from University of Sheffield and Professor Biplab Sikda from National University of Singapore. And in this presentation, I will present our work VFL-GAN, a vertical federated learning-based generative adversarial network for vertically partitioned data publication. And in this presentation, I will take you through the background, problem formulation and research gap, and the proposed VFL-GAN, and experimental results of VFL-GAN. And last I give a privacy analysis of the synthetic data sets. First, I will introduce the background. AI is an emerging technology, and current AI models are data-driven and highly depend on the training data. However, sharing personal data directly is prohibited due to the privacy regulations. And to protect privacy, we can release a synthetic data set for AI purpose. And for example, the cars in the figure are generated by DALL-E, and you see they are high quality and can be used for training an AI model. However, in vertically partitioned scenarios, the attributes of the same users are distributed in different parties. And the data cannot be shared across different parties due to the privacy concerns. And the target of the vertically partitioned data publication is to release a synthetic data set that contains all the attributes from all the parties and without sharing their local data. And for this problem, we have three assumptions here. The first is there are n users in party 1 and party 2, and they are same and can be aligned. And the second, party 1 and party 2 contain different attributes. And the third is the local parties and the central server are honest but curious and non-concluded. And the problem can be formulated as the following. There are m parties, and each party maintains a private data set, and the m private data sets can be combined to construct a new data set X. And we aim to generate a synthetic data set X tilde, where for the samples in X tilde should have a similar distribution to the samples in X. And if we train a normal GAN, for example, WGAN GP in each local party, then we can generate local synthetic data and which has a similar distribution to the local private data. However, the research gap is that the Formula 1 doesn't mean the combination of the local synthetic data to have a similar distribution to the combination of the local private data. And now I introduce the proposed system that solves this problem. And in this system model, the server maintains a shared discriminator, which is the key point to learn the correlations between the attributes across different parties. And in each local party, there is a private data set Xi and a private generator and a private discriminator. And in the training process, the local party transmits the intermediate features of the local discriminator to the server. And then the server returns the gradients back to the local party to optimize the local discriminator and the local generator. And in the inference process, each local party generates a local synthetic data and transmits it to the server. And last, the server combines all the local synthetic data sets to construct X tilde and then release it to the public. And our system model has two objectives. In objectives 1, we want the combination of local synthetic data sets to have a similar distribution to the combination of local private data set. And this is also the objectives of the vertically partitioned data publication. However, when the attribute set is large, the objective 1 is not enough, and we need objectives 2 to enhance the quality of synthetic data sets. And in objectives 2, we want the local synthetic data set to have a similar distribution to the local private data set. And this is the training objectives of our system model. And the objectives one is achieved by optimizing the discriminators and the generators according to the loss functions from the shared discriminator. And the objective two is achieved by optimizing the local discriminators and local generators according to the loss functions of the local discriminators. And we also construct a baseline named VFLGAN base by deleting the two loss functions from the local discriminators to evaluate the effectiveness of the objectives too. And this figure shows the overview of the VFLGAN for two-party case, and we can see that the system is optimized according to the loss functions from the local discriminators LD1 and LD2, and also the loss functions from the shared discriminator LDS. And this figure shows the overview of VFLGAN base, and the system is optimized according to the only loss functions of the shared discriminator. And for evaluation, we use one image dataset with a large attribute set, and 3 tabular datasets with a small attribute set. And we also use 2 baselines. The first one is WGAN-GP that is trained in a centralized manner and serves as upper performance limit for the vertically partitioned scenarios. And the second is VertiGAN, which integrates horizontal federated learning and GANs for vertically partitioned scenarios. And this figure shows the results on the image dataset. And we can see that WGAN-GP shows the best performance since it trained in a centralized manner, and followed by VFLGAN, VFLGAN base, and VertiGAN in sequence. And we can see the performance order is the same under the 2 evaluation metrics. And for tabular datasets, we can see WGAN-GP, VFLGAN, and VFLGAN base show a similar performance and outperforms VertiGAN. And we can have the following conclusions from the evaluation results. First, the performance of VFLGAN and VFLGAN base is close to that of WGAN-GP and better than VertiGAN, which shows the effectiveness of the proposed framework. And the second is for a large attribute set, for example, the MNIST set, the VFLGAN outperforms VFLGAN base by a notable margin, while for a small attribute set, they show a similar performance. And this can be explained. The information loss in the shared discriminator is negligible for a small attribute set. However, when the attribute set is become larger, the information loss become significant, and we need local discriminators to improve the quality of the synthetic data. And also to further protect privacy, we apply a Gaussian mechanism to make VFLGAN satisfy an epsilon delta DP. And the differentially private VFLGAN also present a reasonable performance. However, as pointed out in reference 3, the synthetic datasets are not safe from privacy attacks. And for privacy auditing, we combine shadow model attack with leave one out assumption, which is a stronger assumption than that in reference 3. And we use the attack performance to estimate the potential privacy breaches through the synthetic datasets. And this table compares our auditing scheme with other membership inference attacks. And due to the strong assumptions of our scheme, the AUC performance of our auditing scheme is much higher than the membership inference attack with realistic assumptions. And this table shows the AUC performance of our auditing scheme on the synthetic data sets generated by VFL GAN and differentially private VFL GAN. And from the table, we can see that the privacy breaches of VFL GAN is not significant. And after applying DP mechanism, the privacy breaches become negligible. And we have following conclusions in our paper. First, we propose VFL GAN for vertically partitioned data publication. And then we provide an auditing scheme that applies membership inference attacks to estimate the potential privacy breaches. And also, we integrate a Gaussian mechanism in the training process of VFL GAN to make it satisfy differential privacy. And the privacy breaches through the differentially private VFL GAN is less than that through the VFL GAN. And thanks for listening. Feel free to ask any question.
Hi, thank you for the interesting talk and work. For me, it is not clear how you kind of train the discriminator on the server, and is this some sort of intermediate leakage? Because to train the discriminator, maybe you have to send. Yeah.
I see you mean there should be some potential privacy breaches from the features and gradients in the transmission process.
Yeah.
And actually, in our paper, we also apply a membership inference attack to evaluate the potential privacy breaches of the features transmitted to the server. And the result shows that even for the non-DP method, the privacy breach is minimal. For our auditing scheme. Maybe,
I'm more concerned maybe with, for instance, model inversion that would allow you to kind of reconstruct the original data rather than membership inference.
Yeah, but as we know, the immerse attack is more difficult than the membership inference attack. So if this framework is safe from membership inference attack, then it's very difficult to launch a inverse attack successfully.
Okay.
That's the logic.
Thank you.
Sorry, I didn't notice in your experiment if you show that if they train simply locally their data and then they publish it, it's less accurate or less private. You had in your experiment because they have separate features. If they just train locally again on their own data set, and then they publish the new synthetic data set locally. So I have D1 prime, D2 prime, Dn prime, and then combine them.
Yes.
You have any comparison of that one? What happens if?
No, I didn't compare for the WGP trained only in the local party.
Yeah, because it's vertically. I was thinking maybe it's not that much worse, but yeah, maybe future direction.
Because in my perspective, that doesn't work. Theoretically, that doesn't work.
No?
Yeah.
Okay, thank you.
All right, let's thank the speaker one last time. And now it's lunch, so see y'all.
was coming early, if you can just move towards the center, that would be helpful because then people they can just pick them. It will just more people. Okay. Hello, everyone. Welcome to the really interesting session of credentials, signatures, and sign-on. Our first talk is from Thomas Gross from Newcastle University, and you can see the title, Thomas Gross.
Thank you very much. Welcome to this talk on Simply Tell Me How, on the perceived trustworthiness and technology acceptance of anonymous credential schemes. Now, the big questions for this talk is Quo Vadis, anonymous credentials, attribute-based credentials, how are we doing in terms of adoption? And some of you have been around for quite some while in that topic. We had a lot of valiant efforts to develop anonymous credentials, attribute-based credentials, and they're quite a mature technology these days. So you had Identity Mixer in the beginning, you had UProof, you had the effort in IRMA cards to develop that. You had massive European Union projects like Prime Life or ABC for Trust. And more recently, first adoption in similar technologies like in Privacy Pass or in technologies transferred to Signal. So in some sense, there has been a lot of effort in the community to make this work. And I would have been the first one 15 years ago to tell you anonymous credentials, attribute-based credentials will be pervasive and we will be using them everywhere. However, that's not quite how adoption worked out. So instead of these systems having pervaded technology and user behavior, we're still working on that. And there are a lot of reasons for that. Building these ecosystems is complex. Getting the buy-in of identity providers, of service providers is another problem. But for today, we're focusing on, so what is going on for the user? What decisions are users making in adopting these systems, and what is driving those decisions? So before I start for real, I would like to call out two kinds of works of some of our colleagues. The first one by Zenaida Benenson and her colleagues who investigated anonymous credentials schemes at the time on a smart card at Patras University. What we had here was really good ecological validity, so you had actual cards in the game that students could use. However, it was a small sample and they could only go into correlation analysis. Another line of efforts was by David Harbord and Sebastian Pape, who investigated not credential systems as such, but Jondonym and Tor as privacy-enhancing technologies. And they worked with actual users, so typically having 140 anonymous users involved who actually use PETS out there, and they did a partially square structural equation model explaining 42% of the variance in their models. So what we have seen from this prior work is that the technology acceptance model as a framework that has been used a lot in economics is actually quite a good foundation to look at attribute-based credential schemes. So our topic for today, the aim is, how can we model technology acceptance and perceived trustworthiness in terms of how users make the decision to use these systems? And secondly, we want to go further than what has been done before, which means we are constructing a true experiment in which we are manipulating conditions to investigate to what extent certain factors influence user behavior. And the first one is intrinsic properties. So that's properties of the credential system itself and its provider. And then we have presentation properties, which are talking about how are we conveying this information to the users. Now, the model we have created as an hypothesis is shown on the screen now. So basically, we started from the beginning in hypothesizing that this is how all of this will work. So you have the core of the technology acceptance model on the right-hand side, which basically says that usefulness and ease of use determine the intention to use a system. And as in earlier research, we have distinguished usefulness for a primary task. So that is what the user actually wants to achieve, reading the emails, browsing the web, getting the job done, and the secondary task, which in our case is privacy usefulness. Now, we considered attitudes and subjective norms. And in that realm, the most important point for our conversation today is privacy concerns. So to what extent do privacy concerns influence user decision-making? Then the major antecedent of usefulness is perceived trustworthiness. So do they actually trust the system to use it? And then two novelties we introduced in this kind of a model are facilitating conditions, which means whether users have the knowledge and resources to actually make the system work, to make it run. And the second one is what's called results demonstrability, which entails whether the user can explain to others or believes that the user can explain to others what the results of the system are and what the consequences of using it will be. So how did we do this? I will spare you a lot of details in terms of statistical modeling and just look at the experiment itself. So what we have here is a mock-up intervention. Basically, we've created a website where people could browse and inform themselves about attribute-based credential schemes, which contained a range of pages, contained an opportunity with a download link, and the instruction for the users was to just read through that, get an opinion, and go about their business in the survey later. Now, what we have done here is we manipulated this web page into 24 different pages so that are changing either the intrinsic properties, so who is the provider, this could be IBM, this could be a university, this could be a government, how is the usage and the benefits outlined for the users, and presentation properties in terms of how complex is the language we're using. Are we using technical jargon, or are we using really easy to understand language, basically made for school children? Are there people present on the page endorsing that and hosting the system? And is there a support infrastructure? And the latter two are basically factors that have been investigated earlier as aspects boosting users' trust in systems. So we went about exposing the users to all of those different variations of web pages and had a study structured like this. So we asked a lot of questions in advance about demographics, attitudes, subjective norms. We got them to inspect the web pages, which typically took a quarter of an hour. Then we measured different aspects in a self-report questionnaire, where also the questionnaires we used were validated in advance. And finally, we go into manipulation checks and debriefing. So what did we get from this? The first thing that I'd like to point out is the sample we have obtained. We were sampling on Prolific, so that's a sampling service provider, where we asked Prolific to stratify the sample. So basically, Prolific creates strata with certain properties, so age, ethnicity, gender, and then users self-select whether they want to participate or not. So it's not a truly random stratified selection, but we have some advantage in how the sample is distributed. Overall, after refinement, we got 812 participants. So this is the largest study that has been attempted in this realm so far. And what we got is the following. We created a structural equation modeling, which represents user decision-making really well. I won't go in all the details, but for people who do statistical modeling, a Ramsey of 0.05 is actually very good, and we explain 83% of the variance. So the model really well explains what users are doing. What you have here as a model on the top corona, the privacy concern properties and technology affinity in some ways. You see the usefulness impact on behavioral intention here, and you see ease of use. And I'm just pulling out a few things to make a point. The first thing is that primary usefulness, so how useful the user still perceives this tool for what he actually wants to achieve, is king. So that has the strongest impact on behavioral intention. The second thing is, if you're looking at drivers that are kind of the root of a lot of decision making, two are standing out. One is facilitating conditions, which means that the user finds that they can find support and the knowledge to actually run the system. And secondly, results demonstrability. So those effects are carrying through ease of use, through usefulness to eventually influence the behavioral intention to use the system. So in the paper, you find a lot more details about the model and insights to gain from that, but these are just some things I'm pulling out. So 3 lessons learned. First, never impede the primary task of the user. So learn what the user wants to achieve with the system, design the attribute-based credential system to support that, and do not get in the way. So that's really important because usefulness mediates anything else in terms of privacy concern down the line. Second, help users run and understand the ACS, which means create the conditions that they can learn what's actually going on and how to run the system, make it compatible and help them, and enable understanding in terms of what are the results here, what are the consequences, what are the benefits. So all of that will have an impact. And finally, make it simple. Use simple language, easy to read, and then add some scaffolding in terms of technical content such that they can gain additional trustworthiness from that. So finally, what we have here is an extended technology acceptance model, which explains user decision-making extremely well. As far as I know, that's the best fitting model we ever had, and it could be used in other cases. The message here is simply tell me how, facilitate use and understanding, and keep it simple. And finally, if you want to geek out on how to do the structural equation modeling, mediation analysis, all of that stuff, look at the paper. So thank you very much. I'm very happy to take questions.
Any questions from the audience?
Please.
Yeah, thank you very much for the extended model. Very exciting. I was wondering, how did you verify that they actually understood the text? Because I think you had one measurement where it's about how well they think it kind of protects, like response efficacy, so to speak. But how can you make sure they actually understood?
A very good question. So we had what we called a factual manipulation check, which basically asks the user questions about what they have read. And by that, we could trace whether they have actually read the content and clocked what was in there. Yeah? So that was our measurements that they actually did the task. What's going in the model, however, is the, and that's part of a standardized questionnaire, is their impression how well they understand this. So it's not about, what knowledge does the user actually have, but what influences the user's decision is how much do they believe they get it. Yeah? Other questions?
Any other questions? Okay, let's thank the speaker then again.
Thank you.
Our next speaker is Jack Traore, and he will be talking about compact issuer hiding authentication. Jack Traore.
So, thank you. I will present the results of our paper. And this is a joint work with Olivier Sanders. So our paper deals with identity management systems, and more precisely on anonymous credential systems or attribute-based credentials as introduced in the previous talk. And we show in this paper how to improve the privacy of users of this kind of systems. So the current approach of identity management-based systems is as follows. 3 types of entities are involved: an identity provider or issuer, a holder or user, and a verifier or service provider. So the issuer issues credentials to holder, that is signed attestations on user attributes that the user can then present to verifier later on to prove facts or right on himself. So the verifier just need the issuer private key to verify a presentation token. For privacy reasons, the user should not reveal all his attributes. Otherwise, he could reveal more information to the verifier than those requested by that verifier. The same problem is with the credential signatures. It could be used to trust the user, or worse, to identify the user if the issuer and verifier collude. So the aim of anonymous credential is to improve the privacy of user of this kind of systems. So they make use of specific signature schemes which will allow the user, for example, to hide some attributes that it does not want to reveal to the service providers, and also to hide the signatures of his credentials. So for example, in my slides, the user Bob could, for example, prove that he lives in Bristol and that he is over 18 without revealing any additional information on himself. So the service providers will learn nothing beyond the statements being proven. More precisely, the issuer will not learn how the Bob will use his credentials, and it will have no information on how the credentials he issued are used. The service provider will not be able to identify Bob if Bob does not provide his name to the verifier. He won't learn anything beyond the information that Bob is willing to disclose to the service provider. The service provider won't be able to distinguish two users with the same attributes, and he won't be able to link multiple uses of the same credential. So as I said, anonymous credentials make use of specific signature schemes, which are also called zero-knowledge proof-enabled signature schemes. So with these schemes, it is possible to generate and verify a non-interactive zero-knowledge proof like this one, but in a very efficient way. So for example, the user will be able to hide some attributes that he does not want to reveal to the verifier and prove that he holds a signature from an issuer on the attributes that he accepts to reveal to the verifier. So there are very, very few schemes that support that where this kind of zero-knowledge proofs can be done very efficiently. And the most popular signature schemes supporting where this kind of proof can be done very efficiently are the following one. There is the Kamenisch-Lisanskaya signature schemes, which has been presented at Crypto 2024. The Poinchval-Sanders signature schemes, which has been presented at the RSA conference in 2016, and the BBS or BBS Plus signature schemes, which has been introduced at Crypto 2004 and then improved at in 2016 and more recently last year at the Eurocrypt conference. So BBS signatures are currently being standardized at IETF, and BBS signatures and PS signatures are planned to be standardized at ISO IEC. So this is so anonymous credentials can be considered as a quite mature technology, as explained in the previous talk. So is it the end of the story? Not really, because in standard anonymous credential schemes, the verifier will know the public key of the issuer. Indeed, he needs this public key to verify whether a presentation token is valid or not. This is a real problem because with the knowledge of these information, one can infer a lot of information on the user. For example, if the user used a credential issued by some local authority, for example, a town hall of a small city, the verifier would at least know the area of residence of his user. So a natural question that comes to mind is the following one. Is it possible to hide the actual issuer of a credential within a set of potential issuers? So in other words, would it be possible, for example, for a student to prove, for a user to prove that he is a student without revealing the university where he is studying? So at the CANS 2021 conference, Bobos and Al proposed solutions to these problems. So the solutions works as follows. The verifier will publish the sets of issuers public key, we call it the policy, that she is willing to accept, and will sign each public key in this set. And therefore, it will act as a self-certification authority. And now the user will have to prove in zero knowledge that he knows the credentials that is valid under a public key that has been certified by this verifier. So in their approach, the size of a presentation token and the cost to verify a presentation tokens are independent of the number of issuers in the policy. So in their papers, they proposed a concrete instantiations of their solution, of their approach, based on growth structures preserving signature schemes from Azure Crypt 2015. So their solution is quite efficient, as we will see, but they relies on the signature schemes, which is not widely deployed. So in our paper, we proposed a more efficient solutions, which is based this time on Quantrial-Sanders signature scheme, which is one of the most common tools used to design standard anonymous credentials. So the main novelty of our work is that we do not use a zero-knowledge proof, which leads to shorter presentation token, as we will see. And the main advantage of our approach is that we do not change the underlying Quantrial-Sanders credentials. We just extend the original schemes with one additional element to hide the actual issuer of a credential, which seems to be optimal. So we compare the efficiency of our solutions with the one of Bobos et al. From CANS 2021. And for our comparisons, we use credentials with 13 attributes, and only 3 of them are disclosed. So regarding the size of presentation tokens, our presentation tokens are 3 times shorter. They are very short, even in the paper of in the constructions of Bobos and At, but they are 3 times shorter than their presentation tokens. Regarding the computational complexity, the generation of a presentation tokens took less than 4 milliseconds with our constructions and 6 milliseconds, which is also very efficient. And verifying the presentation tokens takes less than 4 milliseconds with our constructions and 9 milliseconds with their construction. So to conclude, to be truly anonymous, anonymous credentials must hide the identity of the issuer of a credential. Indeed, with this information, it is possible in certain use case to re-identify the user. So we addressed this issue by designing an identity issuer hiding anonymous credential schemes based on one of the most popular signature schemes, the PS signature schemes. And we do not use zero knowledge proof. We instead tweak PS signatures to achieve the issuer hiding property. So there is an interesting open question, which is the following one. Is it possible to design an issuer hiding accreditation anonymous credential schemes based on BBS or BBS Plus, which is the de facto standards in anonymous credential systems?
It seems you already have a question.
Thank you. This is very interesting. Just on your open question on doing this for like BBS signatures without zero knowledge proofs, like BBS signatures for anonymous credentials already have a zero knowledge proof. Like that's like the protocol is, you know, a zero knowledge proof of knowledge.
Yes, but what I mean here is that in our solutions, we do not use zero knowledge proof to hide the identity of the issuer. We use zero knowledge proof to hide the attributes or the signatures, but not for hiding the identity of the issuer. And we would like to do the same because we could use the generic approach of to make BBS plus issuer hiding, but this will not be a standard solution because we will have to modify to use another signature scheme on the verifier sides, and this is what we want to avoid. We want to use only BBS plus and not another signature scheme.
Okay, thank you.
Any other questions? Okay.
So the first question is it a punctual Sanders signature from 2016 or 2018? There is an extension to that scheme. Do you see any barrier for, I mean, bringing the idea to the other scheme or construction?
We use the 2016 version, but we could use also the 2018 version.
Yeah, and also compared to the paper from Bobbles et al., so that one is based on the structure preserving signature, which means that the message is a group element.
Yeah.
But in punctual Sanders, there's a scholar message. Does it make any differences whenever you want to go to the deployment?
Yes, because we do not have to modify the punctual Sanders signature scheme. So punctual Sanders signature schemes will be standardized. So we would like to not really modify these schemes. That's why we propose these solutions.
I got it. Yeah, thank you.
Maybe we can take one more short question, if you have. Okay, let's thank the speaker again. Who's moving the mouse? Okay. Our next talk is from Kilian Demuth about support personas. Kilian.
Thank you very much. So welcome to my talk about support personas, a new concept for tailored support of users of privacy-enhancing technologies. So with current privacy-enhancing technologies, we often have the problem that we have different users that use the same technology. And this could lead to problems like the following, that some users may not understand the information they are given because the target group of the privacy-enhancing technology is an expert group, but also lay users may want to use it. And this could lead to the fact that they don't know what to do, how to use the technology. It could also be that the information they are given is too complicated. Also, they might understand the language, they don't get the concept of the technology, and therefore can't use the technology. And all this can lead to an I don't care for the users. They just don't use the technology anymore because it's too complicated and they don't understand how to use it. On the other hand, we might also have users that ask for more information about the technology and really want to dive deep into it and get to know how does the technology work, or might even want to customize it to their personal user experience. And to address all those different user groups, we developed the concept of support personas. So as you might know, a persona is an archetypical user with different behavior, motivation, and goals. And with our support personas, we try to identify the needs of different user groups to address their needs when developing new privacy-enhancing technologies. And we base those support personas on the privacy competence and the privacy concern of the user. in order to be able to customize the user interface and give the user only the information they understand based on their privacy competence, and also suggest appropriate default settings, because some users with a higher privacy concern might accept an additional overhead when using different technologies in order to protect their privacy more. And users with a lower privacy concern might or don't want additional overhead and want the privacy enhancing technology to work in the background and don't interrupt their workflow. So our methodology was a three-step approach. We started with workshops as a participatory design approach, then build a prototype to be able to assess the support personas in a first development process, and finally evaluate how this worked out and whether we could address the different user groups with our new concept. Yeah, so the workshops, we conducted 3 workshops with 5 participants each, having different backgrounds or different technological backgrounds, so that we can address the different user groups or different groups of end users. And the first goal of our workshops was to create a categorization of users into different support personas. So based on the literature, as already said, we wanted to base the support personas on the privacy competence and the privacy concern. But the fine categorization we wanted to do in a participatory design approach to be able to get the input from the end users to be able to get the result that they are all represented by the final categorization, because that might be a problem if only we as experts might do this categorization. And the second goal of the workshops was, after this categorization was established, we wanted to create the different user interfaces for one privacy enhancing technology. In our case, a browser plugin for the topic of script tracking, to make script tracking more transparent to the user. That was our first, or that should be the first application for our personas, where we test the approach in the development process. So the results of the workshops were the following. The participants of the workshops developed 3 categories for each dimension: privacy competence and privacy concern. And in the second step, said that the user interface of the browser add-on should be solely based on the privacy competence to be able to address, as already said, for example, lay users with more explanations and less details, but also serve experts users with very detailed detailed information, and also a variety of settings. And they also said that the default settings of the browser add-ons should be based on the privacy concern, as already explained by me. So then we built the prototype, and here you see the first user interface for these lay users, where the website the user browses is gets just a privacy score based on the script usage on this website, and the user gets some explanations on what scripts are, for example, how the score is calculated, and only has one setting for disabling this browser add-on in the case the website might break or might not work, so that they can turn off the browser add-on to be able to visit this website. In the more advanced user interface, we call it extended user interface. You see we have a little bit less explanations, but a little bit more settings. And the final or third user interface for expert users provides very detailed overview over the different scripts used on a website and the possibility to block all the individual scripts. But although the users will start only with the user interface based on their privacy competence, we also provided the option to switch between the user interfaces in case a user might want to try another user interface, or might want more information for in specific case. So we also evaluated our browser plugin, and there with this together also our concept of support personas, and to find out whether we could address all the different user groups as we might, or as we hoped. And yeah, our results were the following. So most users preferred the extended user interface. That was the one in the middle. That was expected because most of the users are close to the average user for which this extended user interface was developed. But we also found out that most experts prefer the same user interface in everyday life, but don't want to miss the detailed user interface in case they want to really dive into one website, get to know what scripts are used on a website. But for everyday life, they want the more simpler user interface. And we also found out that the users which liked the detailed user interface the most were mostly experts, except for one case, which also shows that the detailed user interface, as expected or as hoped by us, is mostly adopted by expert users. Very interesting to see for us was that we saw a learning effect for lay users. So the lay users started with the standard user interface with many explanations and less settings. And after reading all the explanations, getting to know the tool a little bit more, trying it out, they progressed to the extended user interface to get a little bit more settings and didn't need the explanations they read at the beginning. And we could also verify this learning effect during our qualitative interviews, where we could verify that the users learned something they did not knew before. And the user experience questionnaire also attested a good to excellent usability for our application, which shows that with the support personas during a development or in a development process, we were able to develop an application with a good to excellent usability for all users. And it also shows that our results were not influenced by a bad usability. Finally, we developed some recommendations for developers on first. So we saw that the needs of different support personas should be addressed by developers of privacy-enhancing technologies to make it easier for all the different users to use the privacy-enhancing technology, and not only for expert users, but get a more broader audience for all the technology we develop. We also found out that the different user interfaces should be based on the privacy competence, but the default values of the technologies should be set according to the privacy concern of the user. And we also saw very positive results that after we involved the users in the development process, which could also be helpful for other developers when developing privacy-enhancing technologies to get the second view of the end user. And for end users, we encourage them to inform themselves about privacy topics. They should be aware that data about them is often distributed to third parties, and therefore they should really think about which data is shared with whom. But this is only possible if we have the privacy-enhancing technologies that make it easy for users to use them and the users understand them. And thank you very much for your attention.
Oh, so many questions. Who should I go to first?
Yeah, thanks for the presentation. Now, what you described, I think, is more or less just the human-centered design process. And I was wondering, to what extent do you think the super personas would change the process we already know? What kind of overhead does it create? Or is it just personas and now we call it super personas, more or less?
Yeah, okay. Thank you for your question. I think the support personas will help the developers to really think about, to have these different personas in mind when developing privacy or privacy enhancing technologies. Although the ideal HCI process of developing technologies, really has the different end users in mind, but I think the support personas enforce this the thought process to not only develop technology for the developers themselves, but also for other users they might not think about.
Thanks for the talk. So when you introduced the support personas, my first thought was that these would be like qualitatively different, as in like different user goals would lead to different UIs. But from what you introduced, they seem to be mostly quantitative in how much detail was shown. So did you consider like a qualitative thing, or is that like not something you would actually see in user demands? Or
so for the different user interfaces, for example, the explanations for the lay users, we try to keep them as mentioned in the first talk. We try to use more easy language, really explain the topics on a low level, which might also abstract the more complicated things. And I think the qualitative difference between the user interface was also thought about during the development process, but it did not transfer during the presentation.
Sorry? Okay, sure.
Hi, can you hear me? Can you hear me?
Do we have a question online?
Yes, there is an online question.
Yes.
Okay.
Can you hear me?
We are listening.
Yeah, I'm talking. You can't hear me. You can't hear me.
Can you please speak up?
Hello? Hello, I'm talking.
I have one last quick question.
Yeah.
You mentioned about the number of participants in the workshop.
Yeah.
Can you tell us about the sampling bias from that, or how to improve it, or the scope of improvements there?
Yeah. So although we try to have participants with different technological backgrounds, we had the limitation that most of the participants were students from the university, so had a higher education, although they had different study backgrounds. So some came from sociological studies and might better represent this lay user without a background in technology, in IT security or privacy. But that's a limitation we had. Yeah.
Okay. Thank you. Thank you very much.
Thank you.
So, maybe we talk. Our next talk is from Mehdi Sadaghat from KU Leuven about unlinkable privacy compliant signatures.
Yeah, thank you so much for the introduction. So this is the joint work with Christian Badercher from Outputs and Henrik Molnar from the University of Maryland. So I'm pretty sure that most of the people in this room are aware of the digital signatures. So digital signatures are somehow necessary to bind a message to its author, okay? It provides us authentication, integrity, and non-repudiation. So there are many examples and applications for this type of cryptographical primitives. However, in this talk, we only focus on financial transaction applications, and more importantly, in the cryptocurrencies. So let's quickly summarize that what is happening exactly during the transaction, okay? In the UTXO cryptocurrencies. So Jasmine and Aladdin are going to create a wallet, and they will receive a key pair, secret key, and public key. So whenever Aladdin is going to, Jasmine is going to send $5 to Aladdin, it gets the public key of Aladdin and then sign the transaction details, the amount of the transaction, and also the recipient ID, and then send it to group of the validators that we know them as the miners, okay? And the miner check the validity of the signature and then make sure if the signature was created correctly by Jasmine in this example. It's not only about the checking the validity of the signature, it's also about checking the balance of the Jasmine, okay? Jasmine might send $100, but she only has $10 in her account. So we have like somehow a transparent fish tank in this scenario, that the balance of everybody in this setting is visible to everyone. So in this scenario and this example, Jasmine right now has $10. She wants to send $5 to Aladdin. And after finalizing this transaction, Aladdin will receive 5 extra bucks and will be top up in his account, okay? Needless to say that having this fish tank and transparent fish tank reveal a lot of information, including who is the pay, who is the payer, and so on. However, it's the pseudonym, is not the real ID. I talked about Aladdin, but there are a lot of research that somehow link the pseudonym to the real ID of the user in the cryptocurrencies. If your employer sends, your salary in Bitcoin, then anybody can see that how much you are receiving. If you are living in Europe, it's not a big deal, but if you are living in US, this might actually be sensitive information. So this is the main motivation behind DApp, is decentralized anonymous payment systems like Zcash, Monero, Tornado Cash, and so on. The identity of the involved parties, including and also the transaction amount, will be hidden in this scenario. It's very important whenever you are making a private cryptocurrency or any other application, it's a very good framework, a place for illicit activities. Money laundering, tax evasion, and so on that you can see in this slide. So the main research question in this paper is how we can find a good balance. So we know that the regulators are looking to avoid such illicit activities in the system. However, the users and service providers are looking for having a good privacy, okay? So we are actually trying to find out what is and how we can solve somehow a dilemma here. There are also some solutions like accountable privacy. Like if you're sending this transaction using Zcash and Monero and everything is hidden, you can also encrypt the transaction detail, and there are some group of auditors that they can open up. But it's not a good solution, definitely. If there is everything hidden, how the auditor can be suspicious to a transaction if they are not going through brute force? And additionally, prevention is better than the cure, okay? So all of these solutions are saying that, okay, the transaction can happen and afterwards they can open up and see who was involved. But we are looking for the prevention in this mechanism. If this is illicit, then it's not going to be finalized. We also have in the real world, it's some substances or some items are limited to some specific buyers only, okay? It's not easy for any random person to go to a shop and buy some radioactive substances, for example. But if you are working on a research lab or some university and you are working for the research purposes, you might actually receive a certificate for this purpose and they can actually buy you this. I want to highlight the importance of the joint policy in this scenario and this example, okay? So we are not only talking about the person who wants to go and buy this item, we also want to talk about the feature and the attributes of the shop as well. This person does not have any restriction for going to the grocery shop for buying other items. So let's again back to the previous example that we had and how we can bring some cryptographic solutions. Maybe there are some other solutions I'm not aware of it, but we are looking for some cryptographic solutions to bring this policy during the transaction validation. So we already talked about that Jasmine and Aladdin are owning a key pair of secret and public keys. And now imagine that we have a policy. We go to the regulator, please give me your policy. If you are concerned about some actions, for example, tax evasion and so on, just provide me those policies. And now we have a setup in the system, okay? It's different from the permissionless blockchain like Bitcoin and Ethereum that we know, but in this scenario, we have a setup for the users. Again, the users receive a key pair, the secret key and public key. And also we want to, as we already talked about, we want to actually have a policy to decide about the validity of the signature as well. So these two properties are necessary in this research. Additionally, we would like to have a joint policy. And also, whenever we are talking about the attributes of the users, during each of these transactions, there shouldn't be any leakage about the involved parties. Okay? And also, imagine that I'm going to send another transaction. There shouldn't be any link between my transactions. This is important also for the privacy purposes. So we are looking for these 5 features and properties in this paper. If you are working on cryptography, you might actually notice some of these features already that are similar in some other cryptographic primitives as well. Like in the digital signature we talked about, it's just about unforgeability of the signature. It doesn't provide any of other features that we were looking for. The closest construction and primitive is policy compliant signature from TCC 21. But the problem is that construction does not fulfill the unlinkability feature. And you can actually track the users based on their transaction in the system. In the unlinkable policy compliant signature, which is one of the contribution of this paper, we have 4 entities. Jasmine, the same, who is the sender. We have Genie, who is the third party in the system that we want to actually issue the secret key for us. We have Sultan, who is the verifier in this scenario. You can think of the verifiers or the miners. And also we have Aladdin, the same actor. We have 5 algorithms instead of 3 that is more common during the digital signature: setup, keygen, rand key, and signing and verify. Let's arrange them in this way. So during the setup phase, Genie gets the policy as an input and generate the master public key and master secret keys. Using the master secret key, it gets the list of the attributes of the involved party that who wants to join to the system and then generate a key pair again, as we already discussed. Both of these parties, not in this image, I mean, this slide, can actually publicly, without being reliable on the Genie side, can re-randomize their key to make completely unlinkable the process without having any limits. And during the signing phase, the Jasmine who wants to sign the message now gets the most recent updated version of the public key of the Aladdin and then used her secret key to sign the message. And essentially, Sultan can decide based on the most recent updated version of the public keys. More importantly, I have to emphasize here that Sultan as a verifier is not going to check a checklist to see that whether the attributes are actually involved in this transaction or in this signature or not. So the ingredients that we are using are zero knowledge proof system, digital signatures, predicate encryptions, and also pseudo-random functions. And also for the instantiation, because we have a very, very detailed proof of concept as well. We have 3 proposals for making these systems possible. And for the digital signatures, we are based on these constructions. I don't want to read them because of lack of time. And also for the predicate encryptions, we are using the OT12 predicate encryption. And so the random function, we are based on the Dodin-Svianskovsky famous construction. And for non-interactive zero-knowledge proof systems, we are using 3 different zero-knowledge proof systems: bulletproof, which is a range proof, Gross-Sahai proof systems, and also we are based on Schnorr. So some of you might actually be worried about, okay, it's very fancy, it's very beautiful to have such a system. How efficient is this? Okay, it's not efficient at all. But I have to emphasize that, so it's like a proof of concept. It's not a full-fledged deployment that somebody can use it. But if you check the 10 attributes for a user, you can see that the signing process is around 5 seconds. And for the verification of the signature, you also need to check the 5 seconds. So it's not good, okay, definitely. But there are some space to actually make it better, definitely, if you are interested to work in this line of research. It's just a proof of concept. We also have 2 other alternatives. We actually implemented the first one. We call it generic construction based on the inner product relations. But we have 2 other policy logic as well. One is the role-based and another one is separable policy that we achieve the constant overhead in most of the cases. So this is the result that actually I talked here. And this is the detail that we actually included in the paper. I totally recommend everyone, if you are interested, please take a look to the paper. What we didn't discuss is the security properties of these systems. We care about the correctness, unforgeability, attribute hiding, and unlinkability. We define them, and we also prove them formally. Additionally, we didn't talk about the detail of those other primitive, the alternatives that we talked about. Also, we have a detailed zero knowledge instantiation in the paper that you can check, and also some other applications. Very quickly, I just want to mention some potential future work, minimize the trust that we are actually relied on the central entity, and also design a better predicate encryption that makes the system more efficient, and also design the same concept and achieve the same property, however, with different techniques. This is my talk. Thank you. Any questions?
Any questions for the authors? Is there an online question? Please go ahead.
Yes. Can you hear me?
Yes.
Oh, great. Okay. So in financial systems like this, the policies generally can't be written as a computable predicate, right? Like the intent of the transaction is part of what makes it legal or not legal, right? So, I mean, where do you even start if your predicate isn't can't be decided just by looking at the content of the transaction?
So yeah, that's true that it's not that much easy to actually bring the regulation. Imagine that you want to bring the GDPR that computer understand, okay? The people even don't understand. And it's really hard to actually bring all of this stuff to the mathematical facts, because we are talking about inner product equations, for example. So actually, I'm not sure if I understand correctly that how we can actually bring the policy to the transaction level. If something is happening on the blockchain is immutable, okay? So we cannot alter it later and bring it back to the previous state. We just want to prevent it because of the integrity and authenticity of the digital signatures.
Right, but when you're deciding whether to allow a given transaction or not because it's money laundering or something like that, you can't tell if a transaction is money laundering just by looking at the transaction.
Definitely, that's a very good point. But I need to emphasize, I mean, there might be some metrics about this, okay? It's not easy, it's not trivial as a researcher, as a cryptographer, that how we can actually transit from the existing concerns in the financial systems to the mathematical fact and cryptographical solutions. But now think about, we can actually define, I'm showing a slide right now, it was a backup slide, that we can actually design some metrics about it. We already talked about the attribute-based credentials. It's a very similar concept. The nationality, the age, and some other concerns can come to rescue, but it's not, I completely agree with you that it's not that much general concept to avoid and understand that is a tax evasion or some other aspect that we already discussed.
Do you have a further follow-up comment or?
No, that's fine. Thank you.
Maybe the author can take the rest of the questions offline. We'll invite the next author, next speaker. Our next speaker is Ivan Krul, who will talk about their ASOK paper about trusting self-sovereign identity. Ivan.
Yeah, so I'm here to present our SOK on trusting self-sovereign identity from myself and my collaborators, Helen Pike, Sushmita Ruz, and Salil Khan here. It's really hard to fit an SOK into an 11-minute presentation, so I'm going to take 12. So if we think about digital, well, I'm warning you so I don't get cornered, right? So if you think about digital identity, honestly, like motivating is kind of a waste of time. I think we're all familiar with it. In Australia, we've set aside $250 million to deploy a digital identity. We already have it in our states. In 2023, Louisiana was one of many states that are now requiring that you authenticate with your digital ID to make sure you're over 18 before you can go to adult content websites. If you flew here on United, you probably were prompted to take a picture of your passport in the app and send it to a third party to verify before you get to the airport, and they'll pinky promise to keep it safe for you, so don't worry. So the obvious question is, are there any problems with this current status quo, right? We're rapidly digitizing, and is there any challenges? And the cartoon I use is a newspaper article from a major telecom in Australia when they had to apologize for losing about half of Australia's driver's licenses in a data breach. So we have some significant problems, right? We had Optus, they lost a lot of information just last week. The ID verification service used by TikTok, Uber, Twitter, they lost all of their data. I think about once a week I find a new article to cite in my thesis, right? It's a genuine problem. And I mean, I'm obviously not the first to identify this. And since about 2017, self-sovereign identity has been discussed as a potential solution to this problem. And it's a very traditional credential exchange. So you have three entities, you have your issuer, and they're gonna issue credentials to an identity owner, and then the identity owner sends those credentials to service providers. And there is kind of an assumed and implicit trust between service providers and issuers. We're kind of making the assumption that there is an existing authority who can issue credentials, right? We already accept governments issue driver's licenses, and we're not really challenging that. The key differentiator is we want to make sure that these credentials are stored in wallets owned by the identity owners, so they have the sovereign control over their self-sovereign identity. And the credentials are just typical attribute-based credentials. So in the example of a driver's license, there's someone's name, their birth date, their address, their license number, who issued it, and some form of digital signature as proof. So my slide was called SSI is a solution, but what is it a solution to? And if you're going to be really pedantic, what is the point of digital identity? And for my convenience, I'm going to use a really simple definition is we use identity and we present it to build trust between untrusting parties. So a service provider doesn't know who we are, so we show them our card going in, right? Like, if the bartender asks, are you 18? Everyone's going to say yes, right? They don't trust us. And we've seen a lot of history and a lot of examples that, as identity owners, we should stop trusting service providers. They don't deserve our trust. So we have two untrusting parties and we need to build trust between them. And all right, now we're getting to the SOK part. In SSI's academic literature, in industry implementations, and existing surveys, there really is no existing definition on what trust means. Either like we're making different assumptions on where trust exists and where we need to build it up, and it's a whole mess. And as a consequence, across surveys, we're missing properties and features in them. Implementations are doing things that don't quite make sense. Industry is implementing things that are just off the rails sometimes. And we don't really have a framework, and we have a pretty limited means to be evaluating these new features. And because this is an SOK, I'm also going to complain about the lack of standardized terminology. So for our contributions, we provide a comprehensive analysis of trust in SSI. We analyze known implementations of SSI, both academic literature, but we also looked really heavily at these industry implementations to see what they're doing. And as an outcome, I hope that we provide a foundational framework for future SSI research and development. And I'll very briefly go over some of the key points. So rather than just talking about this credential exchange, these three parties, we're actually going to talk about a trust over IP stack. We're going to provide a lot more detail. This is sort of modeled over the TCP IP stack. And it's not original from this work, it's from the Decentralized Identity Foundation. So on the bottom layer is the trust support, and it's these public utilities to anchor trust. So I said, we making an assumption issuers exist and they're trusted. How do we anchor them into an SSI system? And that's the responsibility of the layer one. We do this through decentralized identifiers or DIDs, and they're URIs that will be dereferenced to some sort of document with their public key and their endpoints and information like that. Traditionally, 2017 era, this was very blockchain. The DIDs resolved to blockchain. That's not really the case anymore. Layer 2 is not that interesting. We're just using that to communicate, and I'll skip it for time. And layer 3 is trust tasks with a credential exchange. And for everyone in this room who's done attribute-based credentials or anonymous credentials, this should look familiar because it is the same thing. SSI is not proposing something different. We're taking attribute-based credentials and those works, and we're inserting it into this framework. So, credential exchange. And then with the credential exchange, we have these availability for extensions or additional properties. And the two that everyone likes to talk about is selective disclosure and unlinkability. So in selective disclosure, if I'm presenting my credential to a bar to show I'm over 18, they don't need to know my address, right? So with selective disclosure, you only provide the credential, like the claims you need. So you only give your birth date. And then with unlinkability, I shouldn't be tracked across my presentations, right? It's just additional usage information we don't need. So you present in a anonymous way. I'll say that carefully. And then the top layer here is the trust applications. So these are the applications in the governance structures that are actually deploying some sort of SSI ecosystem. So, you know, your EIDAS 2 in the EU is coming out pretty quick, and you should watch out for that. And you know, in Australia, we're rolling out our digital ID. Like, the government is really the entity that's going to be pushing SSI, and they're going to be defining the trust applications. And these applications, they're naturally making threat assumptions. They have some assumed level of trust, and they're naturally going to accept some threats exist. And when you have a threat, it kind of implies there's a risk, right? And then from the risk and from the threat, you need to provide a mitigation. Like, how do we fix this problem? So I'll just give an example rather than talking about it. In the case of selective disclosure, the threat is service providers overcollect identity information. The risk is we have our identity breached, like we always do. The constraint is that identity owners should be able to minimize the data they share. And the mitigation is selective disclosure, which we extensively survey in our paper. So we did this for 11 categories and 16 threats, including identity owner identification, non-transferability, key and wallet management, selective disclosure, unlinkability, a whole lot more. For each of these, there's varying mitigations. There's a whole set of them. If you want to know them, they're in the paper. And then we were kind of left with like this disparate collection of threats and mitigations just thrown everywhere, right? You know, we have selective disclosures, protect us. Why and when do you use it? So we created 3 broad categories, and these are, I'll highlight, recommendations and not rules on what level of trust applications have. So there's trustful, intermediate, and zero trust. So in a trustful application, you know, there's not really sensitive credential data, and we fully trust all the entities, the identity owners, the service providers, the issuers. Yeah. In intermediate, we have quite a bit more sensitive identity data. I think now we're doing like government issued IDs. We don't really trust identity owners as often, so we want some protections against them, right? They're posing some threats. We do not trust service providers as much anymore, please, right? So we have selective disclosure and protect against there. And we still maintain really a lot of trust in issuers. We still assume there is some trusted issuer or set of issuers. Zero trust is a really small edge case that kind of falls into SSI sometimes, where maybe things are really sensitive. We still kind of trust identity owners, but we just don't trust we don't want any issuers. We don't want to trust any sort of centralized authority. And then we provide recommendations from all of our threats and where they would fit into these categorizations. So in the case of selective disclosure and unlinkability, in a trustful model where we trust service providers, we don't need these. So we don't recommend including them. But if your application is subscribing to an intermediate trust or a zero trust model, I would really recommend looking at building one of those. We also, and I'm not going to talk about all of the tables in the slides, we surveyed all of the different approaches to each of these layers. So we have a bit of a catalog of components on the layers and the different approaches to these extensions and mitigations. And then we surveyed a whole lot of academic contributions. We categorized them based on those 3 trust models. And then we looked at like what did they actually implement and compared the 2. And I'll talk about that. And we looked at industry's credential profiles, they like to call it, because they don't want to use the term SSI anymore. Again, what's their trust assumption? What do they actually implement? And we compared the 2. What is academic versus industry doing? And I'll just quickly conclude with a few key takeaways. So first, I want to say this very clearly. SSI is not a blockchain identity system, okay? Industry implementations tend to prefer, and by tend I mean every single one of them, are using traditional public key infrastructure, okay? DID web, they're not using blockchain anymore, so throw that away. For better or for worse, industry implementations are using very generous trust models. Most of them we looked at are trustful implementations with no concerns about the threats posed by service providers. These are the industry implementations they want to use for like the European digital identity and in Australia, so kind of a concern. And there's a really significant and major divide between academic research and industry's implementations on actually where there is trust in SSI. And this is portrayed in my paper, but talking with people who work on these credential standards in industry, it's just a common knowledge that the work SSI academics are doing is just not being recognized in industry because we are so unaligned. Also, across industry and academia, I'll attack both very quickly. Very few works actually address the threats they claim they consider. Yeah. So for future work, please let's be clear on what is our trust assumption. What are the threats actually implied by that? What mitigation should we be doing to protect this? What components are we actually using? What are we implementing? Are we using BBSCL? Where, why, right? And I won't talk about it because I have no time, but it's not lost on me. There's anonymous credential people in this room. Unlinkability is really ambiguous in SSI. The anonymity of anonymous credentials isn't really mapping well to what people think unlinkability is in SSI. If you want to know about it, talk to me or read my paper, but it is an ongoing concern. Thank you. Now it's 45 seconds over.
Hi, I wanted to understand whether you found a connection between unlinkability and duplicate identities, because you mentioned that multiple presentations should be unlinkable to each other. And I think that is directly in contrast with the requirement that you should not, a single person should not have multiple identities.
That's a really difficult question to answer. So like unlinkability is looking at, I'm just presenting my identity to the service provider after I've been issued it. And unlinkability in that case is arguing that service provider shouldn't be able to see, you know, it's the same credential, right? It should be basically a zero knowledge proof. That does not mean that the issuer shouldn't be checking that I'm not collecting duplicate identities. That's a separate discussion, and that's actually a thread in the paper if you read it. Yeah, I could go on too long for that.
Okay, thank you.
I just have a quick question on self-sovereign identity in the W3C DID standards. And I say this as an ex-W3C employee who was very suspicious of that standard. So if no one's using blockchain more, which is probably a good thing, and they're just like servers talking to servers, and the DIDs are just like, hey, it's a redirect to a server. How is self-sovereign identity like in any way decentralized or in any way different than just like handing someone the key with like an OAuth protocol? It seems to be, that's well understood and studied. And like what's different and why can't we spend a lot of time building anonymous credential tech? Why aren't they using any of that tech? Why are they reinventing the wheel with like worse cryptography and worse security and trust properties? It's kind of confusing. They just seem to be using self-sovereign as like some sort of fairy dust to make the stuff more attractive.
Yes, thank you. Okay, why are they? Just to confirm your response, yeah, pretty much blockchain's gone, right? Everyone's using DID web, which is literally just going to a URL and looking it up. Yeah, or like a phone talking to a server client, right? Whatever. And then we're just trusting traditional PKI. Why do we keep talking about blockchain and all this stuff in the academic? Yeah, nothing's really different. But now we are seriously in a position where many regulators and governments are trying to use this, and the industry is actually really on top of it, but academia is not. And we keep talking about self-sovereignty and blockchain and this and that, and we're just arguing into an echo chamber rather than actually being useful. On your topic of OAuth, there is wonderful work by the OpenID Foundation on this. It's OpenID for verifiable credential issuance, presentation, and something else, kind of combining OAuth protocols with the issuance and verification of, you know, SSI credentials. And that's gaining a lot of traction.
Maybe we'll take one more quick question.
Oh, no, I'll just be quick as well. It's the theme of the session. It's a dual question, so it makes it even harder. So first, do you have any insight what's going on behind the scenes that the providers are creating trustful environments and trusting service providers even with the risks that might pose? And the second one is, in your SOC, you largely looked at the kind of low-hanging fruits in terms of selective disclosure and unlinkability, which has been around since 2001 or something. What about the things we really could do with anonymous credentials like predicates? You mentioned them, but
yeah,
where is that going?
Okay, so I really hate to say this, it's fine. Okay, so in terms of in terms of industry's implementation of being really trustful and not caring about any of this, what I've read, because I skimmed the Australian government policy, is they're just going to accredit service providers. So then we're just going to have like a trusted set of service providers, and you need to, as a company, apply to be able to collect identities rather than having like a free and open identity system. I'm not a fan, but it kind of does negate a lot of those issues. And your second question?
The second one is what about the higher end functionality in terms of predicates?
Yeah, so in my SOK, predicates is a type of selective disclosure. So, yeah, thank you.
Let's thank the speaker again. Last but not the least, the final talk of the session from Jan about post-quantum XML and SAML, single sign-on.
Okay. So thanks for coming to my talk. My name is Jan Opitsky, and this is a joint work with Johannes Miller on the topic of post-quantum XML and SAML single sign-on. So it's a lot of loaded titles, so let's parse through it. So let me first briefly talk about XML. If you don't know, XML is a markup language used for data serialization, but a lot of security protocols are XML-based, primarily SAML, which I'm going to be talking about later. There is also like this HL7, which is a framework of protocols that are used by healthcare providers to talk to each other. And there is also this XADIS, which is a IDAS-compliant electronic signature standard. So it's accepted in EU as an electronic signature standard. If you want to do XML, if you want to do some security in XML, you have basically two building blocks, which is XML signatures and XML encryption. And those are there are two separate standards for that. So SAML is an XML-based security framework to exchange information. So it's a set of protocols that kind of have a similar message structure, and they use the messages are XML documents. But the main kind of use case for SAML is to implement a single sign-on scheme. Compared to like consumer-based single sign-on schemes, which are mainly based on like JSON-based OpenID, SAML is heavily used in industry and academia. For example, my university uses it, my old university used it. In Luxembourg, we use it to log into our banks or to our government to like to do your taxes, to see your healthcare receipts and stuff like that. Yeah, so it's heavily, every identity and access management typically supports SAML. And there is also this one prominent implementation, open source, is Shibboleth, which is also used by this In Common Federation, which is a federation of US universities. So you may have heard about it. So how does a single sign-on SAML protocol works? It's very simple. So basically the user wants to log in at the service provider. So we have three participants. We have the service provider, the SP, the user, and the IDP, the identity provider. So the user wants to log in at the SP. He says, yeah, I want to log in. The SP creates a authentication request, which is a SAML message. The user will forward that to the IDP, and the IDP will process this request and begin an authentication. This is kind of out of scope of the SAML protocol. It can be like multi-factor authentication. It can be a passkey. It doesn't matter. But after the IDP completes the authentication, he will issue a response which says, okay, I have authenticated this user, or it failed, and I certify that I did it. And this response gets forwarded back through the user to the SP. He will process the response and potentially issue like a authenticated authorization cookie to the user. From a security perspective, the authentication request can be optionally signed, like the standard doesn't require it to be signed, but the response has to be signed because otherwise the user could forge his own responses and log in to impersonate any user. And there is also optional XML encryption if the IDP wants to send some secret information to the SP, that just the standard supports it. So what's post-quantum? What's the problem? The SAML and XML standards, because they are very old, all standards currently support only classical cryptography. Where what I mean classical cryptography is basically all crypto that's based on the hardness of factorization or discrete algorithms. Unfortunately, Peter Shor in 1994 came up with a quantum algorithm that solves this problem in polynomial time. The good thing is that it's a quantum algorithm, so you need a big quantum computer to run it. So I hope nobody has it yet. But the development is like continually increasing. So better safe than sorry, and let's be prepared for that. Yeah, and the obvious threats are, you can forge signatures. For example, in SAML, you can impersonate any user and you can authenticate as admin and steal private data or something like that. For public encryption, you can decrypt it. And what's kind of also important that you can already begin collecting the encrypted data now and store it. And then when you get a quantum computer, you can crack it later. So that's kind of called the store now, decrypt later strategy. So it may be already happening. So to the rescue comes post-quantum cryptography. Post-quantum algorithms is basically the name for every algorithm that's resistant to the Shor algorithm. They are typically based on hard problems in lattices, codes, hashes, multivariate equations, or isogenies. The main venue where the standardization or development of post-quantum algorithms happens is due to NIST that had this standardization process since 2016. Initially, there have been 60 submissions, but 2 years ago, they announced 3 finalists, which is they selected 3 signatures and 1 key encapsulation mechanism, which is basically something like public encryption. You can look at it. And they are supposed to announce another key encapsulation mechanism that's probably going to be a code-based, some code-based algorithm. So the algorithms are already developed. The trend now in post-quantum crypto is also to kind of hybridize it, which is, what does it mean? Is to combine classical algorithms with post-quantum algorithms. And it has the hybrid post-quantum solutions have the property that as long as one of the algorithms is secure, the whole system is secure. The motivation is that you want kind of the best of both worlds, which is the maturity of classical algorithms and the quantum resistance of post-quantum algorithms. And it's been kind of recently motivated because a lot of post-quantum algorithms have been cracked after 20 years and 10 years of thought to be secure. So the trust in them is kind of not ideal. And it also, hybrids provide kind of a compliance with existing regulations, because they say, okay, you have to use classical crypto, but you want to also use post-quantum crypto. So you can use both, and the compliance officers will be happy. But the problem with hybrid solutions that there is no general blueprint how to do it. For every protocol, you kind of need to have a specific solutions. So our contributions, we have looked at, so we design post-quantum solutions for XML signatures, XML public encryption, and consequently we get post-quantum SAML. For everything, we provide a purely post-quantum solution, which is kind of a non-hybrid, which uses only post-quantum algorithms, and we provide a hybrid solution. We provide a proof of concept implementation with Java. Due to that, we had to fork these multiple libraries, which is OpenSAML, Apache Santuario, and Bouncy Castle, which is the JavaScript, open source Java crypto library. And we provide performance experiments of we tested our solutions, how does it perform. So let me briefly go over the one solution. So for post-quantum signatures, the purely post-quantum signatures are kind of easy to do because the standard is kind of what we call crypto agile. You just switch out the signature for a signature. There is not really much to do. But if you want to hybridize it, it's kind of more challenging. So we propose 2 solutions, which one we call composite signatures and the other one what we call separate signatures. And the main difference is kind of that the separate signatures are what we call backward compatible. And what does it mean? We say that hybrid signature is a backward compatible if it can be verified by a classical only party, which is like a real world example. If you are an IDP, you want to issue post-quantum secure responses, but you have some clients that haven't upgraded their system, so you want to support all of your clients and you don't want to deal with any problems with that. So after you get after you get post-quantum XML signatures and public encryption, you basically get post-quantum SAML with some caveats. And because of these multiple solutions, you can kind of configure your SAML how you want. You can get purely or hybrid post-quantum or backward or non-backward compatible. And you also have to kind of, in the end, select the primitives. So this is an example of like one test that we did. This is the hybrid solution of a non-backward compatible SAML. It's like we kind of simulated what happens when the SAML protocol runs. So there is a lot of like signature verification, encryption. But one interesting thing is kind of like post-quantum algorithms are kind of pretty competitive with classical ones. They have the high bandwidth requirements, but basically like compared to RSA, like they are way faster, for example, than RSA, like because the lattice algorithms are very fast. So there is not much overhead if you want to do post-quantum crypto. So in conclusion, we provide a foundation for securing XML-based protocols against quantum threat. We provide a proof of concept implementation with forked libraries, which can be kind of used to either migrate your SAML system or other XML-based protocols, which it can get inspired. We provide the code, it's linked in the paper or on the program in the artifacts. We did like performance benchmarks, and we also in the standards, we kind of identified a few places where the standards need to be updated because, yeah, frankly, the standards are pretty old, and very complex. So, yeah. So that's it, and thank you for listening. I want to answer questions.
We already have our first question.
Yeah. Thank you very much for the talk. Very interesting. I have one question in terms of if you actually want to deploy SAML, you also have dependencies on secure channels. So you need to have a TLS implementation or something like that, either unilaterally or mutually authenticated. Do you have future plans to create post-quantum secure channels as well?
Yeah, I mean, that's kind of, I skipped because I didn't have time. So like for TLS provides kind of a secure channel between the user agent and the SP, and the secure channel between the IDP and the user. So it's kind of complementary to the signatures, complementary to SAML. There are already existing solutions for post-quantum TLS. I don't know if you know already in Google, if you have Google Chrome and connecting to Google servers, you are already using like hybrid key exchange that you don't have like the authentication, but they have already deployed it with collaboration with Cloudflare. So like post-quantum TLS is kind of a solved problem. I also have a paper like survey of post-quantum TLS, so you can kind of find it. And yeah, so ideally you would be, if you want to say post-quantum SAML, you would be using post-quantum TLS in combination with this. So they would kind of complement each other. Yeah.
Any other questions from the audience? Yes.
Yeah. So about the forks you publish on post-quantum SAML, are there then plans or any plan to merge them with the main library?
So for the composite signatures, that's a kind of they are kind of separate from the SAML and XML. I just implemented it because I wanted to test this solution, and that's already in BouncyCast, so it got accepted. This is based on like an IETF stand. It was a draft, now it's a standard, I think. So you can already use it, for example, to like create the certificate with composite hybrid signatures. So that's already in the standards. And for the other ones, I'm planning to reach out or make a pull request, but I haven't gotten around to it because there is also, I want to make something better. So, but I haven't had the time to it. But I plan to contact the maintainers and collaborate with them and to do it. Yes.
Okay, thanks.
We can take one more quick question, if it's quick.
I have a question online.
There's a question online?
Yeah.
Please go ahead.
Can you hear me?
Yes.
Great. So the backwards compatible, how does that work with like store and decrypt later, right? Like if they don't understand the quantum now, they can't decrypt it now. And if they can decrypt it now, then it can be stored and decrypted later.
Yeah, good question. So that's kind of the caveat I skipped over. Yeah, you can do backward compatibility makes sense for signatures, but it doesn't make sense for encryption because there is no, it doesn't make sense. So,
Yeah, okay.
So you cannot have you cannot have like a backward compatible SAML which uses hybrid encryption. But also in SAML, like the signatures are kind of the I would say the main security mechanism and the core of SAML. The encryption is kind of an additional, and you can also use kind of some, basically, you are right.
So if I'm understanding what backwards compatible signatures gives you is that if an SP has not upgraded, then they're secure as long as no one has a quantum computer in their back pocket today. Exactly. And if they did upgrade, then they're secure even if someone has a quantum computer in their back pocket today.
Yes. So it's if you haven't upgraded to post quantum, obviously you don't know anything about post quantum, so you are not secured. But it's kind of a compatibility compromise that like at least you get the classical stuff until you upgrade, and it's kind of the usability and migration. It helps with this migration. I think that like the IDP can just issue these responses. It's compatible with the standards. That's kind of what it means, that it doesn't. The response is like standardized, so it doesn't. The person that hasn't upgraded, he's not surprised that this message has kind of some kind of unknown things that I can process. So yeah, you are right. Yes, I would say.
Thanks.
Okay, let's thank the speaker again, and one round of applause for everyone who is attending.
everyone. I'm Kyle Chow from the
I alla fall.
Jag undrar om de måste stämma.
Vi måste räkna där också. Det här är helt overkligt. Ja, den var ner. Den var ner. Jag ska räkna. Det var en 726 meter. Vad är p-värdet på det jag skulle fråga? Jag får kolla det sen.
De fick ändå sämsta. Det.
What's the first one?
Det. Så att det är sämst. Bäst är det. Jo. Ja. Jo. Jo. Ja. Och näst bäst är och ett tredje bäst är och näst sämst är
Det är någon, det är så reglerna är där de spelar på. Titta bort korten nu kommer det snart.
Hi, everyone, or subset of everyone. Welcome to the last session, or at least last technical session of PETS this year. I imagine we may have some people trickling in a little bit late from the rump session, given the timing on this one. But in the interest of not running late and not finishing late, I think let's go ahead and get started. So our first speaker is going to be remote, so we're going to again have a recorded presentation and a live Q&A afterwards. This is going to be Kaho Chow from Georgia Tech, who's going to be presenting on diversity-driven privacy protection masks against unauthorized face recognition.
Hello, everyone. I'm Kao Chow from the University of Hong Kong. Today, I'm very excited to share my recent work about protecting privacy against unauthorized face recognition. And this is a joint work with my collaborators from Georgia Tech. Face recognition has many life-enriching applications, and deploying a face recognition or FR system is easier than you can imagine. You don't need to even train your own machine learning model in the whole process. The most important ingredient is a reference database. This database should contain at least one image for each person you want to recognize. The second ingredient, of course, is the FR model. This is supposed to be the most difficult to obtain, but in fact, you can just download any pre-trained model from the internet. This is because modern FR models, they are not classifiers. They can be used to recognize any person even if they were not included in the training process. The way it works is that you just need to send in each reference image to the model, and the model will project it onto a low-dimensional space. What those pre-trained models can do is make sure those images of the same person will collocate in the embedding space, and those of different people will just form their own clusters. Then when you have an image of an unknown identity, you can simply reuse the same FR model to extract the corresponding embedding and then look for nearby images with a known identity. This property in face recognition lowers the bar for anyone to build an FR system, as long as a reference database can be constructed. Misuse or abuse of this kind of models can lead to serious privacy concerns because privacy intruders can construct this reference database by web scraping. In fact, a couple of companies have already done it on a large scale, having reference databases with images of millions of citizens and offering face recognition services without their consent. To combat unauthorized FR, we need techniques that allow us to protect ourselves proactively. And this is where anti-FR solutions come into the picture. Before sharing our photos online, we can pass them to an anti-FR solution to pre-process them, such that when they are out there, may be scraped by privacy intruders to enrich their reference database, they will not be usable. A query image will not be matched to the correct reference images. To qualify as a usable anti-FR solution, it must be effective, especially when we don't know which FR model will be used by the privacy intruder. Also, we don't want to wait for a long time before sharing our photos online, so it has to be fast. Finally, of course, we want to ensure the protected photos look nice. No one wants to share photos with the face being seriously distorted to avoid face recognition. With all these requirements in mind, we introduced an anti-FR solution called PMask. The key idea is to design an optimization approach that iteratively learns a privacy mask, introducing small changes to the facial image to be protected such that the extracted embedding will not co-locate with the clean facial images of the same person. The iterative process should have a clear termination condition to avoid unnecessary perturbations, degrading the visual quality, and also to save time. The learning should emphasize the generalizability to different FR models because we have no prior assumption about which model will be used by the privacy intruder. So given a photo to be shared, we first use existing face detection techniques to crop the regions containing a face. Then each face will be processed independently by PMask to learn and apply nearly imperceptible changes to it. Then we put these protected faces back into the original photo, and the user can now share it online. In the next few slides, I will highlight the key components in PMask, and I will start with how we optimize the privacy mask for a given facial image. We assume that some images of the user are available for PMask to help protect their privacy, and we have access to a reference database of other people, which can just be a public FR dataset. Given a facial image to be protected, we first randomly initialize a privacy mask and applied it to the original image to generate the protected version. This privacy mask will be iteratively optimized. The way it gets optimized is that given a known FR model, we require the privacy mask to protect the facial image by pushing it in the embedding space towards the direction of the closest facial image of a different person. And it must overshoot by a margin. This is captured by the first term in the objective function. The second part is to ensure image quality. We require that the protected image should be visually similar to the unprotected one. For that, we use structural similarity, or SSIM, to measure the differences between two images. The user can specify a budget for quality degradation, depending on their privacy requirement. Both of these parts have a clear termination condition, so once the conditions are met, the protection is done. This is different from many existing approaches. They tend to conservatively set a large number of iterations to maximize the chance of successful protection. So far, I have talked about how to protect against a given FR model. However, our goal is to be effective against unknown ones, because we don't know which one will be used. Here, we use an ensemble approach with joint optimization. The key challenge is which FR models should we choose to form a team, so that synergy can make the privacy mask effective against other models not in the team. To show you the importance of forming a good team, here on the left is a small collection of publicly available FR models. We enumerate all two-member combinations and measure how well each team delivers privacy protection, which is the failure rate of FR reported in percentages. On the right, we can observe that some teams perform much better than the others. If you make a poor choice, the protection can be 60% less effective. But how to find this subset of models in a scalable manner is an important question. We can't just enumerate all of them do some measurements and see which one is better, because it can take forever. To overcome this challenge, we introduce a diversity-driven technique for FR teaming. The idea is that if PMASK is generated to protect against very different FR models, then it is more likely that it will also be effective in some other FR models unknown to us. To find out those different FR models, we use error diversity. In particular, for each FR model in the collection, we use a public dataset to find out those facial images where the model make mistakes. Then, given a team size, for example, decided according to the resource limit, we can enumerate all possible combinations and calculate how much the team members disagree with each other when they make mistakes. Intuitively, we want a team that all members make mistakes differently, and this reflects their diverse internal mechanisms in recognizing faces. The team making the most diverse mistakes will be recommended to generate the privacy mask. We have conducted extensive experiments on face scrub, a popular FR benchmark, and here we highlight the results. More details are available in our full paper. First of all, PMASK can protect against FR models that are unknown during the protection. On the left, we have facial images of 3 celebrities as queries, and let's assume we don't know who they are. Consider the privacy intruder uses a ResNet50 model trained on a VGG face dataset for face recognition. And the privacy intruder tries to use this model with the reference database to find the most similar face to each of the query image. Before looking into the recognition result under protection by PMASK, we can take a quick look at the protection by other existing schemes, including FOX, the first column, and TIPM, the second column. We can observe that under the protection, the privacy intruder's FR result still returns the images of the correct person. But under the protection by PMASK, the third column, we successfully make the FR system to return an image of a different person. The same observation can be made when the privacy intruder used some other FR models as well. Another thing to note is that if we look at those protected images by FOX and PIPIM, especially the second one, it is seriously distorted. But PMASK can well preserve the visual quality of the protected images. For our FR teaming, we visualize the diversity score and the protection success rate for both 2-member teams and 3-member teams. We can observe that a higher diversity score indicates a better privacy protection. To give an example, for a 2-member team, the average effectiveness across different models is about 93% when the most diverse team is used. But when the least diverse team is deployed, the privacy mask is only useful if the intruder used the same FR model, which is unlikely. Apart from the effectiveness, the teaming is also efficient because we don't need any test samples to generate some privacy mask and see which combinations of FR models produce the most effective mask. In summary, this paper introduced an anti-FR solution called PMASK. The optimization of the privacy mask is convergence aware, so we can deliver better image quality and faster protection. We also introduce a diversity-driven FR teaming to strengthen the generalizability to some unknown FR models. That's all for this presentation. Thank you so much.
And our speaker is on Zoom and is available to answer a couple of questions.
Hello, thanks for the presentation. I have a question regarding the running time of the PMASK thing. Is it possible to run on a device? Because if you publish your image online, then you do that, it is not gonna be safe.
Hello, can you hear me?
Yes, we can hear you.
Okay, yeah. So if you are mentioning about the what kind of resources we need to run PMASK, right? If I get the question correctly. So if that
Yes, it is.
right. So for now, we still need GPU to accelerate the whole process. And that is one, I would say, one limitation that we're currently looking at. And actually, we have some recent results showing that we can actually do it in real time, especially trying to learn a more personalized mask to do the protection rather than optimizing one image. I mean, one mask per each facial image.
Was that right? Okay, cool. Yeah, thank you very much. I was wondering, you're assuming a best, or your protection is a best case assumption, or it's under a best case assumption, right? So in essence, you assume that the adversary neither knows that there is any kind of protection or what kind of protection there is, and also your evaluation assumes that there's a huge database within which any identity can hide, right? So it's not like any kind of nowhere near worst case kind of an evaluation. Is that correct?
Right. So thanks for your question. Yes, that's true. And in fact, we did some experiments to explore what if the privacy intruder knows there may be some perturbation or some mechanism that will counter their face recognition. For example, one very famous defense is very simple, like JPEG compression, lossy compression, to try to remove the kind of malicious patterns on the image. So what we find is this kind of defenses are not able, or this kind of mechanism will not be able to remove the patterns of PMAS very significantly. But that is true that it is not the worst case study.
All right, let's thank our first speaker again.
Thank you.
Okay, and our second talk is going to be on Phantomas, probably mispronouncing that, understanding face anonymization reversibility.
Yeah, thanks for the introduction. Can you hear me? Okay. Well, yeah, I'm Julian, and I'm going to present our investigation into reversibility of face anonymizations. So let's say we are a user and we share our biometric data online to gain some kind of utility. For example, we are playing a VR multiplayer game, or we're sharing images of ourselves on social media. And because we care about our privacy, we anonymize that data. So for example, we apply some anonymization method, which even claims differential privacy on the internet. So that method removes half of all pixels randomly, and we think that's safe, right? And well, maybe there's an adversary and they also look at that image and they think, well, actually, if I interpolate all the completely black pixels, then I get something like this again. And on that, I can run just face recognition, and obviously I can identify the user. And that actually works even with other anonymizations, for example, blurring or noise, where we can get significantly close to the original image. And this obviously completely breaks the anonymization. Anonymization has to be a one-way function which removes all the identifying information. And so if we can reverse the anonymization, this kind of worst case failure for it. So this is what we wanted to investigate. We first want to know, well, which anonymizations are reversible and what are reasons why this is happening so that we can avoid it in the future. So what I've shown before as reversing was kind of de-anonymizations which were specific to the anonymization. So we have some de-blurring methods, denoising, or super resolution, which are approaches which we take from the computer vision community. But if we want to investigate kind of generally which anonymizations are reversible, well, we don't have anything for that. So we need a general de-anonymization. And what we do is we use a machine learning model, which is the same architecture which we can train then for any anonymization method. And what we use is a simple convolutional autoencoder with an additional linear layer in the middle, which is purposely a simple design so that we can better understand what is actually going on. So our adversary model is that users share their data publicly, anonymized data, and then our attacker wants to identify the users. And our attacker has some additional access to data. They have other images of the individuals they want to identify, so that they have something to compare to. And they also have an additional background data set with images of other people. And they also have an anonymization oracle, which we can use to anonymize images, just like you might have an encryption oracle in cryptography. And so what the attacker can do with that information is they can create an anonymized background data set, and then they have pairs of anonymized and clear data, which they can use to train that machine learning model which I showed on the last slide. And then when they have that trained model, they can use that on test data to de-anonymize the images before running the recognition method on them. So what does our experiment setup look like when we investigated this? Well, we had the original data, we anonymized it, then we split our data up into two sets, one of which we used to train the de-anonymization, the other one we de-anonymize and then recognize the images on. We test all of this with two different data sets. So we have some comparison, and in total we test 15 different anonymization methods, which were chosen to be representative of different groups of face anonymizations which we found in the literature. In addition to the general model, which I showed you, we also tested some other de-anonymizations, some which was specific to specific methods, but this is something for you if you want to read the paper. We also tested different recognition models so that we don't rely on one and re-report the average of them. We define a reversibility metric, which is defined by first measuring recognition accuracy on clear data and anonymized data, and then de-anonymized will be somewhere in the middle. And then essentially reversibility is how close can we get back to clear level starting from anonymized level. So something with the anonymization which we can reverse perfectly would be 100% reversible. All right, let's look at some results. And we start off with some basics, which are permutations, which are very clearly fully reversible, but which shows that our method actually works and we can achieve very high reversibilities. And then also interesting are, of course, some of the basic methods which you can see every day, like blurring, eye masking, pixelation, and noise, where we find also very significant reversibility scores, some of them actually very high, for example, for noise, where you can show, well, if you use, essentially with the parameters shown here, use them when we can just reverse them and still identify you, which is something to keep in mind. We also investigate some methods based on differential privacy, where we also find reversibility scores significantly higher than what the guarantee might claim to achieve. But we also find anonymizations which are actually irreversible. For example, methods based on k-anonymity, where we kind of layer different faces on top of each other, have very low reversibility scores. And also methods which remove the entire face and replace it by newly generated synthetic ones are irreversible. And now we were interested in, well, why are these methods potentially reversible? And well, if we look at the permutations, well, we see we don't actually remove any of the identifying information, we only obfuscate it. And the obfuscation obviously means that the originally trained machine learning model will not be able to recognize individuals anymore, but the information is still there, and if we put it back in the right place, the identification works again. For the other basic models, we find, well, we do remove some identifying information, but there's still enough identifying information left that we can reconstruct some of the removed information. For example, if you move one eye, well, I can reconstruct the other eye because I know what kind of eye color you have and what it generally looks like. For the DP methods, we see, well, obviously this seems to be a formal guarantee that's in this case not really suitable if you define your neighborhood based on the pixels which are next to each other. We also considered if there is a trade-off between reversibility and utility. So for utility, we based on previous work, we did a user study where we showed participants anonymized images, and we asked them whether the image showed a naturally human being. And then we can plot this in a reversibility utility graph with utility on the x-axis and reversibility on the y-axis. And if there was a trade-off, we might expect to find some kind of trend in this plot. But in fact, we find both anonymization methods like the synthetic generation ones, which have which are irreversible and have high utility, but also anonymization methods which have high utility and have high reversibility. So as I come to the end, some takeaways. The evaluation of reversibility was previously missing when we evaluated anonymizations, but this is very crucial because we find that 11 out of the 15 tested anonymizations were reversible. Some reasons for that were that information was only obfuscated, or that not all information was removed. And we also find some reliance on unsuitable formal guarantees. And for what we tested, there was no trade-off between reversibility and utility. If you want to read more, there's obviously a paper that you can read. If you have anonymization and you want to test whether it's reversible, we have a software framework that you can use for that. And now I'm happy to answer any questions that you might have. Thank you.
Hi, thanks for the great work. It's very interesting. I actually had like a very similar attack from what it seems on trajectories a few years ago. And what we found back then is that for the DP schemes, that actually the reversibility success didn't actually scale with the epsilon as you would expect. And I was wondering if you observed something similar, or if a lower epsilon really meant lower reversibility.
So we aren't necessarily DP experts, so well, I am not. So how we chose the parameters for all of our anonymizations, which we kind of chose trade-offs, which we found where we thought this seems reasonable, this is something that might actually be used. And I think the epsilon values were already kind of insane to figure out something that made sense in this sense. And I'm not sure if there was a clear trade-off where reasonable epsilons would actually mean irreversible. But at the same time, you would expect some kind of trade-off. I think for all of the anonymizations where you have a parameter, if you make the parameter large enough so that there's basically nothing left, then there's nothing to identify from, right?
Really interesting work. So, I mean, you say not all identifying information is removed. Do you have like an intuition which, like if I would prioritize what to remove, in which order would you remove stuff to get good results?
I mean, kind of the point is that as long as you leave something that's identifying left in the image, then that's something to exploit to identify people. So if you want to truly anonymize pictures where there's no chance of anonymizing, you have to remove everything, right? You might get some results that look nice if you remove the most identifying ones, but that's more an issue of, well, then your recognition method looked at specific things and wasn't prepared for the anonymization.
I have a question, which is, if you want to anonymize an image based on this, what's the recommendation? What should people be doing going forward?
Well, to some extent, it depends on the use case. Best case, obviously, to just not share the image, right? So, but if you want to have some utility, if you want to maybe do machine learning on the image, but you don't care about the person, then replacing it with these kind of synthetic faces really should seem to work well. So this could be an option.
All right, let's thank our speaker again. Our third speaker is going to be Sebastian Zimick from Wesleyan University, and he is going to talk about website data transparency in the browser.
Okay, let's get started. Website data transparency in the browser. So first of all, I want to acknowledge all the fantastic students I had the pleasure of working with. Daniel, Logan, Justin, Jude, Owen, Joe. This is not a student. Hamza is from Google, who did all the machine learning on this. I was, glad I could rely on him here, and he did fantastic work. I will present the work here, but really this was a great, group effort. And then I want to acknowledge Raf and David who contributed earlier. So what's the problem? The problem is websites collect data, third parties collect data on websites. And so that is not obvious to users. Maybe they have some intuition, there is something going on, but it is not surfaced to the users. And overall, my work is about making the internet, making the web, making the mobile ad platforms more transparent, making them more private. And so that is the frame for this work here. And current privacy notices don't help with transparency a whole lot. They're often lengthy and time consuming. There's this paper of Laurie Craner, right? It takes whatever, a year to read all the privacy policies or something like that. And then they also do not always accurately describe actually what's going on. Right? There's a disconnect between the written statements and the software. And so we thought, why not put into the browser a system for dynamic privacy notices? And this should have two effects, we hope. First of all, people are better informed and have more trust in the websites they visit. And secondly, there's also an indirect effect that site operators actually better understand what is happening. Because often there is a disconnect between them and the third parties that they integrate, right? I was many times in the situations where I asked a web developer, hey, there's something going on your website, and they said, hey, great that you tell us, we actually were not aware. And so indirectly, this also helps them to understand what is going on and establish better practices. Now, we developed a browser extension to simulate the in-browser behavior, which we call Privacy Pioneer. And essentially, what it does is it tells who receives which data. So we have a party, first party, or the third party receiving that type of data. The website receiving GPS location data. Amazon receiving email address. And these are four groups of analysis that we do. And the most important parts are the ones where we actually apply a machine learning model, which is for the location. So why do we do that? Well, for example, if your city is disclosed, if, I'm here in Bristol and I find in the web traffic Bristol, well, does that really mean this is my data? Or could it be maybe the website that I visit is from Bristol? Or I'm looking up the weather in Bristol or something like that, right? So how do we tell whether a certain data item belongs to the user? And for that, we use a machine learning model. Just briefly, here's the deterministic way how we do it. We do essentially URL list matching, regular expression and attributes. And then we do the machine learning using a tiny bird model that we put into the browser, which is actually also not trivial. So you need to carefully think what do you analyze, and how much performance impact do you have when somebody is browsing. We listen for HTTP messages while someone is browsing. We filter and search for target values. So for example, my IP address, my email address, my GPS data. Try to populate that as much automatically as we can for the user. We store that as evidence, and then we try to match that to what we see in the HTTP responses and requests, and then we create privacy labels. And so that's how these labels look like. And then if you wanted to know more, if I click on location, then you see a more detailed privacy label like this. A short word on performance. This is it. So for city, for example, we have here an F1 score of 0.84. Region works better. Latitude and longitude in the 90s. And so overall, 0.94 is the F1 score on this. And I thought I give a brief demo. There's always a high risk something goes wrong, but at least it might be funny. So let me try to go ahead here. I've installed here Privacy Pioneer, and you can do that as well. So if you're interested, you can go here to this GitHub repo, privacy-tech-lab privacy-pioneer. There you will find everything, and you can get the add-on on the Firefox add-on store. We currently only support Firefox. And then you would have this little rocket here in your extension bar. And so what I have here, just a site that the student sent me actually earlier today, no affiliation or anything. I should also say I have not checked these results. So I believe we're doing a good job at being accurate, but I would need to manually check that is actually correct here. A small note, what I also interestingly discovered, they give you a little note here that they respect GPC. So some sites do that as well, and I could actually opt out. I don't do that for the time being. I have not interacted with this site at all. It is, as it is. And so now I can click on this little rocket here, and it analyzes what's going on. And for example, here, it tells me there's a first party and there's one third party that collected my location data. And so I can click on this, and that gives me here an overview. And that's the site itself. It collected the precise location. That means like GPS location and a more coarse location, and also the city. And then there's a third party, drift.com, that did the same. And now I can click on this, and I can find here, for example, this is my latitude and my longitude. I was not asked in browser, right, to give access to that kind of information. I can demonstrate that to you. Like if I go to my settings here in Firefox, like here are the location settings, and I can check here bamboo. There is no, I did not give such permission. So I imagine what happened is they sent my IP address to a third-party service, and then got back the matching GPS data and city and so on and so forth. And that's how they determined my GPS location. Let's do a second example, Internet Movie Database. So I go to this Internet Movie Database, and actually I need to do something else before. So here I can do a watch list. So I can enter also a custom keyword that I would like to track. You can do anything that you like, but can be also phone number, email address, street address, whatever you want. I say Batman, because that's important to me. If somebody knows that I'm a fan of Batman. Okay. So what was the recommendation? Oh, I didn't do the type. Excellent. I'm so glad, I'm not alone here. See, this is the thing, my students, they did so much fantastic work, and you can see, how little I did. So there you go. Thank you very much.
Now Batman, we have that now. And so let's go back actually to IMDb here. So if I now look up Batman, I'm searching for Batman, I'm interested for the Batman movies, then I would also see, okay, what happens here now with Batman, and that is under the personal category. And so here we see two third parties. They receive my keyword. This one is obviously affiliated with Amazon, AmazonAdSystem.com, and also Scorecard Research. I don't know if they're affiliated with Amazon or if that's a totally third party. And then you would also see here, okay, this is the context. This is either the response or the request that contains here Batman. And I could do the same here for the Amazon one. Well, it tells me, okay, this is from imdb.com, GDPR, consent, it gives various information here, and also this keyword, that was sent, to the third party. So this is, this little demo and how that works. And maybe I show one final thing that you could do. You can look all, everything that really happened here. So this is like a browser history, but for privacy. It keeps, all the information, and you can then, check, okay, what the websites were doing. If you don't want to see this, immediately in a pop-up, it will be also stored here in this interface. And so these are, the three interfaces that we developed: the pop-up, then this history, and also the watch list. We did a usability study on that. I want to say a few words on that. Okay, I don't want to share that. We guided people through 3 tasks. So we told them, for example, enter this keyword, go to the site, explain to us, what are you seeing? Do you find that useful? And so on and so forth. And then people filled out a survey. And so here are some of these results. Overall, 82% strongly agreed or agreed that privacy pioneer was useful or easy to understand, rather. And there's some differences in the pop-up, in the history interface, in the watch list. And then whether they found it useful. It's about the same number. 90% of people either found it very useful or found it normally useful. And so that suggests that would be something that people are interested in. So overall, what to make of this? Well, we need more transparency. I'm preaching to the choir. Privacy analysis in the browser can help with that. It's accurate and feasible. If you want to try it out yourselves, all the code is publicly available. The machine learning model is publicly available. Maybe a slight, kind of going into the future. What are we going to do? Well, we want to crawl the web. And actually over time observe websites from different geographies. So what's happening here in Bristol, what's happening in the US, what is happening in Korea, and so on and so forth. Are different privacy practices there in different countries? Do they change over time? And that's why we developed this crawler based on this analysis. I'd like to acknowledge the support provided by Google here, and the additional support provided by Wesleyan University and the Anil Fernando Endowment. And with that, I'm happy to answer any questions.
Probably only have time for one question, and I saw your hand first.
Thanks for a very cool extension. And I would be curious about how you believe that this BERT model works for things that can be obfuscated, because websites can use obfuscation, or they can at least encode it in like base64, and then BERT doesn't seem like the tool to solve that. Can you comment a bit on that? Namely, by your evaluation, was it also including such examples?
Yeah, that's a very good question. So basically what we do here is, that's, for example, relevant for email addresses because they are often encoded, for example, right? And so we apply common encodings like base64 and protobuf and so on and so forth, and then try to decode that and then run the machine learning model on that. But we have not tried to run it on the encoded string, and I don't think it would work, but then again, who knows? We haven't tried it.
Okay, one more question.
Hi, thanks for the great talk. I wanted to ask if you think, how does this compose with server-side tracking? So would you be able to detect it? I think my guess is that you wouldn't really, but.
Yeah, I don't think so either. I think, I mean, we are just looking really at what goes from between browser and server. So no, we're not really looking at that. I think maybe there is some kind of hint of that, because you are like, depending on what you do at the front end, then the back end may change, right? I mean, you may see different advertising based on the data that you give in, but that's nothing we are tracking here.
All right, let's thank Sebastian again. Our fourth speaker is going to be David Hasselkeist. I think I got that close. Sorry for mispronouncing everything. And he's going to be talking about raising the bar, improved fingerprinting attacks and defenses for video streaming traffic.
Okay, so plain encryption is not sufficient to protect your privacy, and I'll tell you more why. And today I'll present our work on raising the bar, improved fingerprinting attacks and defenses for video streaming. This is joint work with Ethan Whitwer, August Karlsson, Niklas Johansson, and Niklas Karlsson, where Ethan and Niklas Karlsson is also here in the room. So online streaming is estimated to account for almost 70% of the internet traffic today, and the content that we watch can reveal much about our thoughts, opinions, and interest. It is important that users should be able to obtain independent information without an adversary either controlling or monitoring this information, and an adversary capable of disclosing even a small fraction of which videos users are streaming can have significant privacy impact. As an example, streaming represents a major source of many people's daily news, and the disclosure of this can result in targeted political misinformation. Like here we have the political ads during the 2020 presidential election campaign collecting personal information and spreading misleading information, or we have political campaigns targeting you on Facebook. We also have censorship examples in the streaming domain, like China censoring a top live streamer on the eve of June 4. We have Malaysia ICE censorship powers over Netflix, and we have Amazon's Twitch banning some channels after researchers finding pro-Russia propaganda. So traffic analysis generally refers to inferences that can be made via observable patterns in encrypted communications, where the goal is often to extract user behavior, online activity, or communication parties. It is a form of metadata analysis where we assume the payload to be secure and instead analyze the packet sizes, packet timing, as well as the direction, so the metadata. And here we assume a local passive adversary monitoring the encrypted connection between the client and the server, and this includes a broad range of potential actors, including malicious users on the same local network, as well as the internet service provider. An attacker collects traces of packet metadata and uses a machine learning classifier to determine which video is being watched. In the context of video streaming, one can easily see here in the plot how streaming leaks sensitive information, where we show the encrypted traffic of 3 different video streams for 3 different videos. And they are streamed using something that's called variable bitrate, which adjusts the bitrate based on the complexity of the video, where scenes with minimal motion or static images require lower bit rates, whereas action-packed scenes require or demand higher bit rates. And combined with something that's called dynamic adaptive streaming over HTTP, also known as DASH, each video is broken up into segments of the same duration, but with different sizes, making the pattern of one single video quite unique. And this pattern can then be used by an attacker to identify which video is being watched over the network. But despite the threat, few defenses have been proposed, and these often highlight only a single feature like segment size or segment intervals. And none of these accept or provide acceptable trade-offs between 3 important factors, which are protection, overhead, and quality of experience, leaving users exposed. Therefore, in our work, we present the first extensive study of video fingerprinting defenses, and we do this by beginning by applying website fingerprinting attacks to video traffic, and then we implement video fingerprinting attacks from prior work. Next, we adapt two website fingerprinting defense, front and regulator, to work with video traffic and also assess their effectiveness using simulations as well as live deployments. We propose Scrambler, which is a defense that achieves competitive results against all of the evaluated attacks that we evaluate. And we do this by having a moderate overhead, high quality of experience, as well as significant protection. And finally, we collect and release the dataset long enough, which is a dataset, large-scale dataset containing network data, as well as QE metric data in varying network conditions. So in our work, we evaluate the use of 5 different attacks, with the first 2 being website fingerprinting attacks, where we evaluate deep fingerprinting, also known as DF, as well as TikTok. And for video fingerprinting attacks, we evaluate leaky streams, walls have ears, and viewed and burst. And when using these attacks on our undefended dataset, we are able to achieve pretty high results. For example, pretty high accuracy. So for example, here at the top there, we see if we attack for about 15 seconds, or if we eavesdrop on the stream for about 15 seconds, we are able to achieve 83 or 92% accuracy, depending on if you're using DF or TikTok. Whereas if we listen for a bit longer, 43 seconds, we can increase this accuracy up to 97%. And for video fingerprinting attacks, if we eavesdrop on the stream for 60 seconds, we can achieve over 90% accuracy, whereas Beauty and the Burst is notably stands out with 99% accuracy. So how do we defend against these kinds of attacks? Well, we have these kinds of defense mechanisms where the first thing we can do is simply to add dummy traffic. And these are padding packets that are indistinguishable from those carrying real application data. And this, of course, comes at the cost of additional throughput. We can also add packet delays, and of course, this comes at the cost of additional latency. But using these defense mechanisms, we can form some defense strategies, with the first one that we consider in our work is random padding. And the idea with random padding is that we simply apply a heuristic that randomly inserts packets throughout the stream. Or we can use some constant rate or regularization, where we both delay and insert packets to achieve some form of constant rate. And we can use this, different fixed rate windows to regularize or have different constant on different parts of the video stream. And in our work, we evaluate the use of 4 defenses, as well as when not applying any defense. And this is undefended. We have constant rate, we have adapted front, where we adapt the defense front to video traffic. We have adapted regulator, and we also have Scrambler, which is the defense that we propose. Now I'll quickly walk through these and their results. So for the first case, where we have undefended, here we show the throughput, as well as 4 different quality of experience metrics over time. At the top, we have throughput, we have buffer size, as well as live latency, as here we are considering when we are watching a live stream. We also have the playback rate in blue there at the bottom, where the optimal playback rate is, of course, at 100%. And we have the bit rate, which is the quality of the stream, where the optimal is the maximum quality, and in this case, it's 4 megabits per second. So at the top here, we see that the throughput varies over time, creating a unique fingerprint for this specific video. In the middle, we see that the buffer size fluctuates just below the targeted live latency of 3 seconds. And at the bottom, we see that the playback rate is set to 100% after some initial adjustments. And quality switches only occur in the beginning, and the stream is being played at the maximum quality of 4 megabits per second. And in summary, with undefended, we get high throughput, no overhead, high quality experience, but of course, we have no protection. Moving on to the constant rate. So with the constant rate defense, the idea is to send packets at a constant rate on both the client and the server side, and the rate should be the same for all the videos. So here at the top, we observe a steady rate of traffic with some content-independent throughput drops due to some machine limitations. And in the middle, we see periods with temporary pauses and stalls in the playback, which causes an increase in the live latency, the orange line. And this in turn causes the playback rate to increase, the blue line at the bottom, pushing the live latency down towards its target of 3 seconds. And as the live latency decreases, so does the playback rate, eventually reaching 100%. But in summary, with the constant rate defense, all attacks become completely ineffective as we achieve an accuracy of only 1% over 100 videos, which is basically, in this case, random guessing. But we have high overhead, and quality of experience is degraded with wait and stall events. Moving on to our adapted front defense. So the idea with adapted front is that we adapt the website fingerprinting defense front, but to video traffic, where we simply repeat the front defense over a continuous stream. And this results in a cyclic pattern of cover traffic throughout the video stream. And here we see that the quality of experience is unaffected by the defense, and the playback is almost always at the highest quality. And this is because front does not delay packets or inject enough padding to exhaust our link. But with adapted front, we observe that it provides very poor protection, with accuracy being around 73 to 99%, depending on the attack, and even if we are using unreasonable amounts of overhead. But the good thing is that quality of experience is not impacted. Moving on to adapted regulator, where the idea is to adapt the website fingerprinting defense regulator, but to video traffic. And here we are maintaining a rigid traffic pattern, which is less strict than the constant rate, which we can see at the top plot there. And this results in low attack accuracy, moderate overhead, but we can see through the bottom plot that we have very poor quality of experience with wait and stall events and excessive number of quality switches. And this highlights the importance of evaluating not only a defense performance, but also its effects on quality of experience. As in this case, we have good performance in terms of attack accuracy, but very poor performance in terms of quality of experience. And finally, moving on to our proposed defense, Scrambler, which we consider is a hybrid defense. The idea here is to regularize packet timing within segment transmissions and randomize segment sizes as much as possible by having padding traffic after each segment. And our proposed defense, Scrambler, provides a more acceptable trade-off than the other tested defenses, with attack accuracy being significantly reduced depending on attack or much randomness, all the way down to 6%. We have moderate overhead, which is much less than the constant rate, and we are able to achieve high quality of experience. So to conclude the presentation, in our work, we have presented the first extensive study of video fingerprinting defenses, where we first began by applying website fingerprinting attacks to video traffic, and we implemented video fingerprinting attacks from prior works. We adapted 2 website fingerprinting defenses, front and regulator, to work with video traffic, and we assessed their effectiveness with both simulations and live deployments. We have proposed Scrambler, which is a defense that achieves competitive results against all of the attacks that we evaluated. And we have moderate overhead, high quality experience, and significant protection. And finally, we have collected and released Long Enough, which is a large-scale dataset containing both network traffic and QE metric data in varying network conditions. And our work shows that there is pressing need for more attention to fingerprinting defenses. With that said, more details are in the paper, and which can be found online, and I open up for any questions.
Thanks a lot. Very nice talk. I'm wondering, so your adversary model implies video on demand, right? Because if you have live streaming, then the adversary cannot pre-train any templates or whatever. So you have video on demand. Did you consider prefetching instead of having cover traffic that is just like dummy traffic? Because if it's video on demand, you could prefetch future segments, right? And then you don't need any additional overhead other than that.
So with video on demand, yes, you are correct. We can prefetch the segment sizes, or sometimes you can even calculate the segment sizes beforehand. But in our work, we actually do live streaming, and we assume that the attacker in this case would collect the traces, train on it, and then classify it afterwards. So the data set or the streaming is based on live streaming in this case.
You mentioned you were doing your experiments with 100 videos. Obviously, there are more than 100 videos available for streaming. Do you think that these results would extend if you were trying to do these attacks in a like actual online environment?
I mean, yes, the results would probably still hold. I mean, this is evaluated in a closed world environment where similar settings as website fingerprinting, we are using a world of around 100 websites or around 100 videos, but we can also evaluate in an open world where we would classify on streams that are beyond these 100 streams. But in many cases, yes, the results would still hold.
Wonderful. Thank you very much. All right, our next speaker is going to be Niklas Carlson, who is also from Linköping University, and he's going to be talking about StyleAd, a usable privacy framework against facial recognition with adversarial image editing.
Thanks. So I'm here to present our work, StyleAd, that the current title is a usable privacy framework against facial rec. Oh, sorry. Typical rookie mistake. I was telling my son, who's at the front row, let's try another one. That this is one of those times when I get nervous, and apparently I make mistake when I'm nervous. So for PhD students in the room, also the senior people get nervous and make terrible mistakes. Anyway, so let's get going. So what I'm here to present is StyleAd, so a usable privacy framework against facial recognition with adversarial image editing. The thing I can add here is that we're doing different type of editing here. So we're doing both semantic editing and residual editing, and I will get into this in a little bit. Now, most of the credit, or probably all of the credit for this, should go to my former PhD student, Minha. So he was the one that came up with the idea, did the work, etc. And I just enjoyed really interesting conversations with him. Now, one of the things that he wanted to do was, okay, we have images, maybe we want to upload them somewhere, and similar to previous work. But what he recognized was that a lot of people, they make edits to these images before they upload them. And then the question was, could we leverage that somehow? So, I mean, one way you can do an edit is, like my son maybe would do, just to replace my face with a Pokemon. And maybe that would be good enough. But this really reduces the utility of the image. So what he wanted was something where we make small edits to the image, but then keep the utility of it. So one of the things that he came up with was then StyleAd. So a robust adversarial editing tool against facial recognition with a high image quality, with emphasis on high image quality. And then he had this idea, well, we can do semantic editing and sort of try different things where we do editing in different latent spaces with the help of these GANs. And turned out that we could do different ways of doing that, and we have it in the paper. The one that we're probably most proud of is this novel residual attack, so where we do residual editing. So that I would consider that as sort of a second big contribution. And then through these contributions, we offer then an integrated user-friendly platform for editing privacy. So we're providing a framework where you can upload an image, you can edit it and put it on your social media. And then hopefully they don't retrain. And because then, as we've seen with other works, with retraining, it becomes a little bit weaker. But as long as it doesn't get retrained, it's a quite efficient framework. In general, we demonstrate better performance over other adversarial methods. Okay, so what does StyleAd do? Well, the basic idea is, again, we take images, and we run them through Stylad. We do some form of editing, maybe sort of make a person smile a little bit more, or we do the residual editing where we sort of just do minimum impact on the image. But the idea is that an unauthorized facial recognition system should not recognize us on those images. Okay. So, and in general, we target then embedding based facial recognition systems rather than some prior work I've looked at classification based. And we're trying to maintain image authenticity. Our method is a little bit different than data poisoning. So we're trying to do a little bit of edit, and then the freedom that the edits give us, we're trying to leverage that to sort of evade these trained facial recognition systems. We do it again in two different ways. One is with the semantic editing, and the other one is with residual edits. With the semantic edits, we have a few different versions. One where we have non-guided, so we just, you can imagine that we saw before how we had an optimization function. So we also have an optimization function where we're trying to move the identity using some embeddings far away from the original identity while keeping sort of high image quality. And then we have some measures for what's good image quality. And then we have one where we do attribute-based editing. So now we take, say, I want to smile a little bit more in my image, and then I'm using that one. And then the third one is we're moving towards a target identity. And with the help of that, we can also then achieve some good results. Okay, so that's sort of the focus of the talk. Now, what is our threat model? Well, similar to previous work, we recognize that there's a lot of facial recognition systems out there. Let's use one of those models. So we essentially download one or two or multiple. We're not looking at ensembles here. We're just looking at, we take one of them, but we try with different ones. And we can, in our framework, we can just pick one out of many. And then we put our optimizer on that using these different criteria depending on which type of editing we're doing. But then we're also recognizing that some systems we might actually be able to query once or twice. And similar to how the first paper had sort of a threshold, okay, when we've done good enough, we stop. So we have a stop criteria based on just a few queries. So when we beat it's good enough, then we might quit early if we can do queries against it. That's not always possible. And in those cases, we just use a different model for the stopping criteria. Okay, so the solution approaches is either semantic editing, which is the framework that we see here, or where we have non-guided, attribute-based, and target-based. But in some sense, we're essentially just picking out different things in this chain to formulate our loss function, and then we optimize it on that. For the residual attack, we're leveraging a few other things, and the optimization function ends up laying on a few other things. But again, it's just an optimization that do some tweaks to essentially what we're doing with the edits we're doing to the images, and then hopefully tooling the facial recognition system. And then again, we have a stopping criteria. Okay, so some example results. This is the original result, or sort of original images that we then tweak, that have different difficulties in terms of what we do with them. With a non-guided, we get really quick convergence, but not necessarily satisfactory results because we're losing a little bit of control. With the attribute guidance, so say I want to smile a little bit more, or I want to narrow the eyes a little bit, then we get a better balance and better protection, which was sort of our initial intuition. And then with this residual, we're sort of getting higher quality result with fairly quick convergence. And again, then it's more sort of the hidden noise. So some of you have worked with focus where you just put a lot of visible noise. And what we're doing instead, we're looking at the noise that we see in latent space, and we're playing around with adding noise in latent space rather than in the visual space. And that's essentially the idea behind the residual. And because of that, we get much more visually appealing results than we get with focus, for example. Okay, so then if we look at sort of, or how good of an accuracy we now are, or how successful we are to fool these things. With the residual, we are able to fool in most cases on 2 different data sets. For those that are familiar, you can guess based on the acronyms. And for latent space or the latent attacks, if you group them together, the accuracy is, or success rate is a little bit less, but still quite competitive. Okay. Now, if you compare with related work, so we have our original images at the top here. We have focus. Again, we add a lot of visible noise. It looks like I wouldn't put that on my website. Semantic adversal, also, it's a lot of visible things. With the residual that we're quite happy with, it looks more like the original faces. And it looks, we don't see any sort of visual sort of bad things happening. We still have some adverse effects, but much less. And then we have our latent edits where we have to pick something to change. So the edits becomes a little bit more visible than the residual. But in general, if we look at then, I'm claiming that sort of visually they look better. So if we take LPIPS, MSSM, and MSE, we can see how the residual attack have much lower values than if we take focus, semantic advert, etc., and also better than on latent. If we look at sort of protection against verification distance, for several of these facial recognition systems, we're beating them. There are some cases where we have focus winning on what it's trained on and semantic advert doing very well. But in general, we do quite well on, and especially then on the aesthetics, we get high quality images. In general, we're robust, provide robust protection. So essentially we see no significant reductions in the pairwise distance compared to no defense. So if I put out the no defense, which is to the far left in these ones, we can see that regardless of which defense is added, it doesn't do us much harm. What is doing us harm is when we actually let the attacker retrain on our data. So when we have an adaptive defense, so using model retraining on the modified images, then our success rate go down a fair bit. So we can see here towards the, I guess, out here, that it goes from, say, for the latent edits, for example, it's go from 99.7 to 35.9, but we're still beating the competition. So, for example, with focus and semantic ad, we get, they're essentially doomed when you're doing retraining on them. And I guess others have seen similar results. Transferability, so if we train on one model and have another one as victim, we essentially do fairly well. So essentially here we're showing the average normalized pairwise distance compared to the threshold. So if we're doing a higher value than one, we're sort of pushing the identity far enough, and we seem to do that even if we train with one and compete against another model. So in conclusion, we've developed StyleAd for facial privacy protections through adversarial image editing. It's robust and user-friendly framework that you can try out yourself, that combines semantic editing and these residual attacks and facial recognition systems. It achieves realistic and high-quality images and provides successful attack rates. And then through our work, especially with the residual, which is the part we're maybe most happy with, we sort of show that there's some advantage with using this residual information in the editing. And again, that's the bottom half of this image that you find in the paper. And in general, we outperform prior work. You can find the code and easy to run Colab examples on Minhas. GitLab. And that concludes my admiration of Minha and his work.
We probably have time for one question. I think there's one in the back.
Thank you very much for your work. I find it very impressive to know that we can change a few pixels in an image in my photograph, and then I upload it, and the facial recognition system is broken. And I wonder about your certain ethical implications of telling people, well, maybe actually not you, or maybe people reading the research saying, yes, of course, we can tweak a few pixels and it's gonna be fine. People go now and say, oh, you can wear a funky sweater, and like facial recognition in the streets is not going to work. People do similar research on like training generative AI model. You can fool the system, etc. But actually in the real world, you don't really know like if the ML model is going to change a bit, they're going to change the training system. So what is the ethical implication of research like this?
So just one thing before I answer. So we're not necessarily changing things in the image space. I mean, we see them in image space, but we do the modification in latent space, and then we regenerate the images so get these more synthetic images that were mentioned before. But yeah, I think with all of these things, there's it's very tied to sort of deep fakes, and I can now sort of edit an image to look like somebody else, and then, but I think many of those things the tools are getting out there, and it's more the uses of them, and I don't think we're gonna be able to stop it. Like the deepfakes are already out there. I wouldn't trust any movie or image, for that matter, that I see online, because the quality is getting so high. And maybe we are contributing to the bad side, probably to some extent. Our hope here is to actually not do that, but rather just providing anonymization tools rather than effective tools to target that somebody is somebody else. So we're hoping we're still on the good side.
All right. Thank you very much. Our final speaker for the final session of PETS 2024 is going to be Yasha Irabanchi, who is a PhD student at the University of Michigan. And he's going to be talking about Privacy Lens, which is an on-device PII removal from RGB images using thermally enhanced sensing.
Is it good? There we go. Hi, everyone. So yeah, last talk, last day. I'm Yasha. I'm from the University of Michigan, and today I'll be presenting Privacy Lens. Cameras are one of the most expressive and information-rich sensors, and they've been incredibly effective at performing important tasks in the home, such as health monitoring, activity recognition, and fall detection. And commercial cameras, commercial products exist that have cameras to do things like elder care monitoring, baby monitoring, and pet monitoring. However, there are privacy issues that exist with cameras. And first, many users have this mental model that the data that's coming off the camera is for their own personal use. And there have been numerous incidents that have revealed that this, in fact, is not the case. And the way that these systems are designed, it often makes it really challenging to determine who exactly has access to this data. And it's partly because the typical IoT pipeline has data leaving the device, going to a server, and on the server, both authorized actors, like the device's manufacturer, and unauthorized actors, like hackers, can get access to the data that the users thought that they were only privileged to. However, even authorized users can perform unauthorized behaviors where sensitive data ends up on social media or online forums. So for example, the owner of this camera-equipped Roomba, they did not expect that photos of them on the toilet would end up on the internet, let alone leave their house. So cameras are great sensors, but people are apprehensive about using them due to the privacy leakages. So how do we keep the good stuff of cameras, the useful parts of cameras, while addressing the privacy issues? So the Roomba's photos were sensitive, they were stored on the cloud, they were accessed through authorized channels, so the annotators. Yet ultimately this led to privacy issues. So how can this be addressed? How can we move past the all or nothing behavior that cameras have, where you either get a whole image or nothing at all? How can we robustly remove PII from an image? But most importantly, how can it happen on device so that the raw data is never stored or transferred? If the Roomba is still sending raw pictures online so that sanitization can happen elsewhere, it still can present a privacy issue. So one way is for this IoT device to have a PII filter on device so that the PII is removed before it leaves the device and heads off elsewhere to cloud storage. Ultimately, no matter how secure the cloud is, people are generally uncomfortable with sharing sensitive data or having it stored on the cloud, and they don't want it to be in a place where someone else could access. So to tackle this problem, we present Privacy Lens. Privacy Lens uses a hybrid RGB and thermal approach, where we can use these two cameras together to create a subtraction mask. And the RGB is used with a lightweight YOLO V5 model that allows us to find persons in the RGB image and create a bounding box. And the union of these two regions defines the pixels to be removed in the RGB image. And using these capabilities, we can selectively composite different image representations, and this allows us to have flexibility between the privacy desires of the user and also the information needs of a downstream application. So, for example, here is some real-time video, and this is a stick figure where only a stick figure representation is captured. Here's thermal subtraction, where persons in the image are removed entirely. And here's face swap, where faces are replaced in the image. But again, all of these need to happen on the device, so we can talk hardware. So Privacy Lens consists of three major components. There's an RGB camera, a thermal camera, and a Jetson Nano. And this Jetson Nano has an embedded GPU on board that allows us to do efficient GPU operations. And we use this to accelerate our PII removal tasks so that they can be done in real time. So in our thermal subtraction and facial landmark benchmarks, it significantly outperforms embedded CPUs, which struggle to maintain real-time performance. But more importantly, GPUs can do these tasks very efficiently, and so power consumption is an extremely important parameter in IoT applications, and Privacy Lens is low power enough to be integrated into existing IP cam fixtures. So to evaluate Privacy Lens, we conducted a deployment study where we deployed Privacy Lens in 3 environments. First was an office atrium, the second was a home living room, and the third was a public park square. And in total, we collected over 22,000 image sets. And of those 22,000, 3,261 contain persons in them, and that forms the basis of our evaluation tasks. So to these images, we applied 3 PII removal methods. The first was the Privacy Lens hybrid thermal subtraction approach, as seen in the top right figure. And we applied 2 RGB-only methods as baselines for comparison, as seen in the bottom 2 figures. The first is YOLO V5 in the bottom left, which presents a lightweight approach that can run on the embedded device. And the second is Dictactron 2, which is a state-of-the-art approach that would require desktop GPUs. And in these example images on the right, we can see that Privacy Lens robustly removed the persons in the image, while YOLO removed most of the person in the bottom right, but failed to remove the person sitting on the sofa. And Dictactron 2 successfully identified both persons, but similar to YOLO, it leaked skin color in the bottom right as the bounding box was not drawn sufficiently enough to remove all PII. So to evaluate these PII removal methods, annotators evaluate the images for whether they contain 5 forms of PII, specifically face and skin and hair color, gender and body shape. And we base these PII identifiers on the California privacy laws definitions, but given the fluid nature of privacy, there can be more work done in this area to kind of define an actionable PII remove metric. And we found that RGB-only methods struggled to remove all 5 forms of PII, only completely sanitizing less than 57.6% of images. And this was often due to partial detection, so kind of in the last image you have some exposure. And also leaving which leaves large parts of the person exposed. Or the RGB-only method failed to detect the person entirely, which would expose all 5 forms of PII, and we define this as a total failure. So YOLO in particular had a total failure in 14.6% of images, and Detectron 2, which fared significantly better, had a total failure in 3.1% of images. Conversely, Privacy Lens's hybrid approach, where we use the thermal image to find people, performed much more robustly, completely sanitizing 99.1% of images. There were no total failures, no facial PII leakage, and the skin and hair color PII leakages were primarily due to insufficient thermal masking. So in this figure on the right, these are 3 example images where our annotators flagged as having PII leakage. So, and we've highlighted them in pink. So in the left, it was some skin color, in the right with some skin color, in the far right. Sorry, in the middle with some skin color, in the far right with some skin color. So while we've shown that Privacy Lens can remove PII well, we also wanted to demonstrate that PII sanitized images are still useful and it can support important camera tasks. Thus, we ran a study to evaluate the performance of these PII sanitized applications. So for exercise tracking, we used the stick figure to identify key points. So in the figure on the right, you can see the key points are matching the squat, and we can use these key points to count the number of repetitions. For the hand-to-object detection, we paired stick figure thermal subtraction and a YOLO object detector. And this allows us to determine when a person is interacting with an object in the environment, so we can understand what is happening in the environment without capturing the pixels of that person. And for fall detection, since fall detection models are very computationally expensive and cannot be done on device, we can generate key points on device and send only those key points to an off-the-shelf model. And that off-the-shelf model we did not have to modify. And this allows us to run privacy-preserved fall detection that can leverage existing machine learning approaches, and we can safely distribute the computationally expensive parts to the cloud. So these are just 3 applications. There are more applications that could benefit from these representations. For example, in a public event or in a line at a coffee shop, you might want to count the number of people without capturing or revealing their identities. These 3 were just the ones that we presented and evaluated in the paper. So I wanted to quickly mention that there's a lot more in the paper, and I couldn't cover everything in the talk. So some things were a threat model analysis and how Privacy Lens addresses them, an analysis of more aggressive RGB-only PII removal methods, how removing PII impacts the performance of downstream applications, how participants viewed the additional Privacy Lens modes and their acceptances in the home, and finally, our limitations and some avenues for future work. So in conclusion, Privacy Lens made the following contributions. The first is the Privacy Lens system, which performs robust real-time and on-device PII removal. The second is an extensive evaluation across multiple environments, showing significantly improved PII removal rates over RGB-only methods. And finally, 3 applications which demonstrate Privacy Lens's utility and their compatibility with downstream computer vision and machine learning approaches. So I want to wrap up with thanking my collaborators, Tom, Will, Professor Shin, and Professor Sample. And I also wanted to quickly mention that I'll be on the job market this fall. And so I'm looking for academic and industry research positions. So if you found this work interesting or want to chat about privacy-preserved sensing or privacy-preserved hardware, please reach out or come talk to me after the session. Thank you.
Hey, thank you for the talk. So I worked on gait recognition before, and just from the motion alone, you can identify people. So when I see your stick figures, I imagine you probably can still identify the persons which are in the video. Have you considered that for Privacy Lens?
Yeah, so we thought about this with Privacy Lens a lot because gate is one of those biometric identifiers that the CPRA lists out, but gate is very hard for an annotator to be able to like point out through a set of images. And so one of the things that we thought about is what if we could lower the frame rate, right? If you lower the frame rate of the gate, you might be able to reduce the presence. The other thing is you can always roll back to thermal subtraction, which does not capture any of the key points. So it's really kind of comes down to what the user is sensitive towards and what the application really needs. So you kind of can't do fault detection without kind of capturing the key points. So you kind of have to accept that gate is going to be a part of it if you want to do that specific task.
Yeah, just a quick note on the frame reduction. That's probably not going to help. We tested that in a paper in PETS last year, and that didn't work at all.
Okay, very quickly, very nice presentation, thank you. Did you tested only on static cameras, did you test any on cameras with motion, also not motion in the camera, but in the view, but motion of cameras?
So we primarily worked with static cameras, but we don't see a necessary reason that a motion camera would have an issue, except for if you have like synchronization issues between the thermal camera and the RGB camera. But that's more of an engineering effort and less of a research effort. But I don't really see as big of an issue with as long as the thermal and the RGB images are synced.
I think that's all we have time for. Before we wrap up, the organizers would like me to remind you that there are going to be closing remarks in the main lecture room in 15 minutes, followed by an awards reception over in the humanities foyer. So with that, let's thank Yasha and all of our speakers again.